physicien de Trieste. Voilà, sur une colline.
Hello, everyone.
Hi, Matteo.
Hello.
Hello.
Hey, Matteo.
Hello.
Good, we have our chairman. Hi, Radek.
Yeah, exactly. Hi. Shall we start or shall we wait a little bit?
Then I would say let's wait a few more seconds.
Yeah, 45.
Yeah, 45.
Minutes, yeah.
Gary, we are going to steal all your ideas. They are on the whiteboard behind you.
Try to blur the background.
What can you see? You can only see the list of papers that I'm supposed to write. And I did this over 2 years ago, and I did half of what I hope to do in 1 year. So not too bad. There's some with you, Andrea.
Maybe we can start now, I would say.
There's one with
Yes.
Radek, which
Yeah, exactly. Yeah. Good afternoon to everybody. My name is Radek Wojtak, and it's my pleasure to chair this session. So the main we're going to focus on machine learning applications to galaxy cluster mass estimation techniques. And up to my knowledge, this is the first fully dedicated to machine learning session in our community. So it's something really special. So we have 6 talks, 1 review talk, and 5 contributed talks. So the rules are as usual. So I'm going to show you when you are supposed to finish your talk. Yes, I think we should go right away to the first speaker. So Michelle Ntampaka, who is going to give a review talk on machine learning for galaxy cluster cosmology. Please, the virtual floor is yours.
Thank you so much. I appreciate it. Everyone can hear me. Everyone can see my slides. Everyone can see my cursor. All right, wonderful. So this is going to be heavy on the machine learning side of things. So I am not going to get an opportunity to say everyone's favorite tagline, which is galaxy clusters are the most massive gravitationally bound objects in the universe. Okay, I had to say it, it's code. But now let's talk about ML and focus on that. Machine learning, what is it? So here's how I define machine learning. Machine learning research explores the development and application of algorithms that find patterns in data. That, I think, is the most important bit, algorithms that find patterns in data. In astronomy, machine learning can be used to do a variety of things, reducing scatter by using complex or subtle signals. I think that's actually going to be a theme of this particular session. Classifying objects, identifying data clusters and finding outliers, generating simulated data and helping us make new physical discoveries. And so now I'll move into what I think is a little bit of a bold claim, maybe not for this conference, but I believe that astronomy is the ideal sandbox for machine learning. I think it's the perfect place to do ML. Why do I think that? First, we have minimal privacy concerns. Unlike something like patient records, where you're worried about protecting somebody's health data, our photons carry almost zero privacy concerns. Astronomy has a culture of sharing our data, especially the very expensive data built with large collaborations. We have well-posed questions. We enjoy public interest and support. Our data sets are non-monetizable. They cannot be turned into an algorithm for selling something. And while that doesn't exempt us from ethical concerns, I think we enjoy a lot of freedom in astronomy for exploration and development of new pattern finding algorithms. And while astronomy may be the ideal sandbox for machine learning, I think one thing we as a field need to wrestle with is machine learning the right tool for astronomy? Is this the right tool for the kinds of things that we want to do? And so over the next couple of minutes, we're going to be exploring 3 questions. So in the short term, one thing I think we need to really be asking ourselves is, can machine learning be trusted? Can we establish proper standards for interpretability? Can we understand failure modes? Can we establish sufficient trust in our training data? Okay, now looking out maybe 1 to 2 years, I anticipate this shift over the next couple of years. Can machine learning be used to make new physical discoveries? Can these tools point us to things that we might not have investigated on our own? And then on longer timescales, 5 to 10 years, what role will machine learning play in the future of astronomy? What skills should we be developing? And what methods should we be keeping an eye on? So we're going to go short timescales to long timescales, starting with the one we should be asking now, which is, can machine learning be trusted? And the first thing I want to do is disabuse you all of the assumption that machine learning is a black box. In fact, machine learning is not a monolith. What I'm showing here is this beautiful algorithm cheat sheet, just a flow chart for scikit-learn, where you can think about a task you want to perform. You go through and answer the questions, and it will suggest an algorithm for you. If you're particularly interested in looking at the details of this, I recommend just Googling this phrase right here, scikit-learn algorithm cheat sheet, and maybe bookmarking it, because it is a phenomenal resource. But I put this here because the algorithms in this space vary to their degree of black boxiness. They vary in interpretability. They can tackle a lot of different questions, but machine learning is not a monolith, and it does not need to be treated as a black box sort of across the board. To build trust in ML models, we need to treat it not as a black box, but we need to understand our simulation details, and we need to approach suspicious results with scrutiny. So here I'm showing something I did by accident. So I was training a model to learn a thing, and the details of that thing are not important, but you're seeing in these 2 figures the true value and the predicted value. In this case, I was learning sigma 8. On the left, I have some results that I believe to be trustworthy. They are at about the theoretical limit for the data set that I had given it. That's about as good as I think I can do. On the right, a model that I trained that accidentally did a factor of 10 better than the theoretical limit. After I trained this model, I woke up, I checked the results. I was immediately tremendously suspicious that I had forgotten my error bars. I checked, they are behind those points. Spent the day digging. And what did I learn? That case on the right, my model had exploited a simulation artifact. It had found some detail in the sim that was not true of reality. It had latched onto it. It had used it to get phenomenal results. But of course, this result won't generalize to the universe. So I took this, of course, did not bundle that suspicious result up as a Nature paper. Instead, bundled it up as an appendix, as a warning to the larger community for some of the ways that these things can go sideways. All right, to build trust in ML models, we need to understand our simulation details. We need to approach these good results with scrutiny. We also need to establish standards for interpretability and failure modes. And so here I have a picture of a horse, and I would like to ask everyone who's on right now to drop in the chat. How do you know that this is a horse? And I think, unfortunately, I can't see that chat right now. So I'm going to, this will be a trust fall for me. How do you know that this is a horse? I will make some guesses, or maybe Radek, you can read some for me. Yeah.
It looks like other horses.
It looks like other horses. Yeah.
Head and tails.
Yeah.
Like a horse. It has 4 legs. That's a
brilliant
feature.
Brilliant.
From prior experience of horses.
Yes.
I've seen horses in real life, and it looks like a horse.
Yes. Okay.
4 legs, long head, long tail.
Now it's a shame we're not in a physical room, because I could probably make eye contact and find this person immediately. I suspect they'd be in the back of the room, and they would suggest it's in a field.
Yeah, exactly.
Is that on there?
The green field. Yes. Yes.
I love this answer. All right. So how does machine learning know that it's a horse? You might come up with a similar list of answers. You might get more of these sort of green field kind of answers. There's a white fence behind it. There's this really beautiful paper that explored this question, like why is a horse a horse? And in their data set, they found one feature was really important for identifying that this was a horse. And the feature is not on this list. The feature was a copyright stamp in the bottom left-hand corner that had been produced by a particular horse photographer that contributed a large number of the labeled horse photos in their data set. So here is that figure. Top left, you've got a horse, you've got the copyright stamp. Here's a heat map showing where the important information is. All right. Scary, you remove this, it is now no longer classified as a horse. Even more frightening, you add that copyright stamp to this picture of a convertible, and this is identified by the algorithm as being a high probability of a horse. All right. So I'm showing you this picture of horses, but what I really want to drive home here is, for astronomy, if we want to build trust in the community, we need to establish standards for interpretability. We need to understand failure modes. But I also want to highlight that even for deep machine learning, we don't have to accept these models as black boxes. There are interpretability schemes that we can pursue to understand what's going on underneath the hood. And to borrow this slide that was presented yesterday by Hank, I think it's so important that trust and understanding be at the forefront of our research. All right, we think carefully about the tasks we want to accomplish and the level of trust that is appropriate for those tasks. I think appropriate is the word I want to highlight here. It has to be appropriate for the tasks, right? There are certainly data reduction steps that I never ever look at between telescope and computer. And there are pieces of the puzzle that I trust other people in the community to do. So I think we need to look for understanding, but at the appropriate level for the task we're looking at. Okay, this is the question I think we need to be answering today. Now, on shorter timescales, I think we should be asking, can machine learning be used to make new physical discoveries? There's 2 ways I see at the moment that this can be done. By asking questions of our algorithm. So we talked about one. I'm going to show you a result in a couple minutes. We talked about the horse example and asking, what has my machine learning model's attention? A second one we can ask is, if I make small perturbations to the input, what happens to the answer? Let's explore number 2 first, and we'll go in reverse order. All right. So here I have a picture of Buzz Aldrin on the moon. Give this to an image classification algorithm, and if it's doing its job correctly, it will say that this is an astronaut. But then we could ask, what kind of small perturbations to this image would cause it to be classified very differently? And here is the answer. Here are some small perturbations to this image that might cause it to be classified as a dog. You see that the hoses on Buzz Aldrin's chest have turned into a dog. It might be classified as a street scene. You can see some street along here. There's a wheel of a car and a number of pedestrians that do not appear to be wearing appropriate gear for being on the moon. There's a little bit of a terrifying two-headed bird here. All right, so I've just asked, how should I change this image to change the answer? Here's for a more astronomical picture. The Crab Nebula might be classified as a nebula. How should I change this to change the answer? And this one's, I think, even more terrifying. If you can see this, we've got a sort of a giant chicken here. There's a dog down here. If you can see very carefully up in the corner, there's a spider web, some pretty terrifying animals along here. This is Google Deep Dream asking this question, perturb the image to change the answer. You can apply it not just to these kinds of images, but to regression tasks of galaxy clusters. So here's a result from a paper of mine from 2019. The machine learning algorithm was asked to estimate masses from X-ray observations. So I think the subject of the next session. It was then asked to increase the mass of some previously unseen cluster by adding some photons. That was the machine learning's task. Then the human task, this one fell on me, was to evaluate where the photons were added. And the result is shown over here in this figure as a function of radius. What's the fraction of added photons? And you can see that it's pretty much ignoring these cluster cores. Okay. Ben beat me to this by about 12 years. I was 12 years late to this party. In 2007, one of his papers showed that cores were sort of a noisy place with respect to mass, and that by excising the cores, you could get a lower scatter mass proxy. All right, but this is enticing because it means that by taking machine learning and evaluating it, we can point toward physics and kind of look and see where the ML algorithm is peaking. So again, unfortunately, I was very late to this party, but it is a nice confirmation that ML is paying attention to something meaningful. All right. Here's another one. This one is under review at the moment. So if you're more interested in this particular result, reach out and we can talk. But this one is an ML-aided discovery of a new self-calibration mode. So the machine learning was asked to calibrate masses of a simulated cluster sample, both with and without weak lensing for that absolute calibration. This was an X-ray sample, so it had that volume limited and flex limited sample that sort of stitched together at the middle. The human task was then to look at the model's attention. This is similar to the horse picture. We're just going to look at where the model is paying the most attention and then just go digging and see if we can figure out why. What we found is that as a function of mass, where is the algorithm's attention? When it has weak lensing data for calibration, it pays attention pretty much to all clusters equally. When it does not have weak lensing data, it pays attention to the middle mass range, right around where my volume and my flex limited samples were stitched together. And this led us to the discovery of a new self-calibration mode for X-ray surveys like E Rosita. Great. All right. So what role will the machine learning play in the future of astronomy? Now we're looking, 5 to 10 year timescales. I believe that machine learning and astronomy can and should move forward together. What I'm showing here is, as a function of year, the error rate for a particular image classification competition. These are for the winners, the top couple of winners. And you can see that in 2011, the error rate was about 30% for the winners. And in 2012, most of them were still about at 30%, but there was one real serious good outlier. And then you can probably guess that a bunch of folks jumped on that bandwagon, and you can see, sort of a slow burn in from there. Okay, this was a big paradigm shift. This data point right here is AlexNet. It was not the first deep convolutional neural network, But the first one that got some pretty serious attention, and it shifted the way we do image recognition. Similarly, astronomy has these beautiful and well-posed questions that can allow machine learning researchers to develop algorithms to address them. And I think there's a real opportunity here for the two fields to push forward together. We have these lovely, rich upcoming data sets. Rubin, deep survey over an enormous sky area. It's become kind of the poster child for big data astronomy. We'll produce about 15 terabytes of data per night. And I think machine learning is a great option for identifying interesting targets for follow-up observation. eRosita, I'm really looking forward to the all sky survey results. And I put this one on here to emphasize that machine learning is not restricted to big data. eRosita will find clusters with 50 to 100 photons, and machine learning can address this question of pulling signal from noise. And Roman will produce a large area imaging survey that will include clusters and cluster environments. And I think there's a really rich opportunity for interpretable machine learning for cluster cosmology there. For algorithms, I'm really excited about something like style transfer. So this is a result. This is an image from the Google AI blog. We're seeing here a picture and then styles painted onto that picture. So Shipwreck of the Minotaur, Starry Night, and the Scream all painted onto this picture of houses. And you could imagine something that was brought up yesterday was this question of, can we build simulations that have the right physics? Perhaps with something like this, we ask a different question. Can we build simulations that cover a variety of physics and then we marginalize over it? Could you imagine having some base sim and then painting on different physics models to produce realistic mock observations for a variety of different underlying astrophysical regimes? Pixel recursive super resolution is another one that I'm really excited about. So, you know, in the sort of true crime TV show, or the crime TV shows where they say enhance, and all of a sudden they pull a ton of information where there was nothing before. This one sort of is a little bit of a call to that. So in the left panel, the input, in the middle, the machine learning algorithm's estimate, and on the right, the ground truth. Before you get too terrified, let me tell you that this thing knew it was looking at faces. You can't produce information where none is. But if you know you're looking at faces, you can roughly reconstruct with some knowledge of where hair and eyes and lips typically go. All right. Now, this is a really neat result from this paper, but you can actually find biases in the training sample. And I mean biases in a couple of different ways here. So I think we all probably recognize who is on the left-hand image, and he looks nothing like the one on the right. And I put this here both as a callback to ethical considerations of ML, but also as a reminder that we should be careful with our training set, because that can bias our results. If we have a monolithic training set, we should expect monolithic results. And I will conclude here. We talked today about how astronomy is the ideal sandbox for machine learning, but we need to wrestle with whether it's the right tool for astronomy. On the short time scales, we need to ask, can it be trusted? Recognize that not all of ML is a black box. Critically evaluate training data in sims, approach extremely good results with scrutiny, and build trust with our interpretation techniques. On longer time scales, we need to ask, can it be used to make physical discoveries? Some ways that can be done is saying, what happens to the answer when I perturb the input, and what has my model's attention? And longer time scales, what role will machine learning play in the future of astronomy? I see machine learning in partnership, not in competition with traditional methods, and lots of opportunities there for us to move forward. And with that, thank you, and I welcome any questions.
Thank you. Let's thank Michelle, for a wonderful talk. And time for questions. I encourage young scientists, PhD students, postdocs. I have the first one, Gary.
Yeah, that was a very nice review, Michelle. Thank you very much. It's good to know you now. So I have a two-leg view of machine learning, and you'll tell me if it's correct.
Okay, good.
It's probably more than that, right? So one is I work in versions, right? Try to go from the data, which has a limited dimensions, to the real life, which has more dimensions, right? And Hadek does this and many others. And so we go through all this math and physics, we tear our hair, and then these machine learning come in and they say, look, if you can train on a simulation, we can do better than you and much faster. All right. So this is a little bit annoying, aggravating. And so it's good to hear from you that in the end, the classical techniques should not disappear and they should work hand in hand.
Yes.
And so here I have a pretty negative view of machine learning, even though I have to admit they do better. Okay. And then the second view I have is there are problems that are just incredibly difficult. One is detecting clusters, okay, from photometric data. You know, that is incredibly difficult. And there are many things in the data that we cannot think about in our modeling, okay, which the machine learning will pick up. For example, I heard an excellent talk by Emmanuel Bertin, where he showed that to get photometric redshifts, the fact that a galaxy has another galaxy nearby in the same image will influence the machine learning and will give you 20% higher accuracy on your photometric redshifts. So I think that difficult problems cannot be solved without machine learning. It's just too difficult for us. We're stuck. We have to go with machine learning to solve these problems, and cluster detection and the full cluster cosmology pipeline might be one of them. I don't know what you think about this.
I agree with you. I mean, I think machine learning is a tool, but it is not the only tool in the toolbox. And you need to think carefully about what are we trying to solve here? Do I need to sift through a ton of data that would take a team a decade? If so, maybe machine learning is the right answer. Do I want to understand sort of the physical underpinning? I think there's a space there for machine learning and traditional statistics to go hand in hand. And so, you know, I am very rah-rah ML, but, you know, use it in the right place at the right time for the right questions in the right ways, not just as a cure-all for everything. Yeah.
Okay, we have time for two more questions. Shantanu.
Yeah, so I guess the traditional machine learning algorithms developed by the computer science community, they do not incorporate or account for error bars or errors. Okay, whereas in astronomy or physics, as such, there's a lot of errors. Maybe this is not that much of an issue in deep learning. So, is that going to be a hindrance in the application of machine learning to astrophysical data in general?
Yeah, this is a really good question. So there are machine learning algorithms being developed to deal with error bars. And I think I might be putting some words into his mouth, but I think Matt Ho is actually going to give a much nicer answer to this question in his talk than I could briefly hear. So perhaps I will give a slightly unsatisfying answer, which is yes, there are algorithms that are being developed and used that can handle error bars, and stay tuned for a longer answer about that.
One more question, Marina, please.
Yeah, hi, thank you. So it was really very interesting review. I asked a question in the chat more about ethical concern. And my question now is, can we find a way to use machine learning to discover stuff we don't know yet?
Yeah, such a good question. So on that flow chart right at the beginning, there were some techniques for data clustering and identifying outliers. And what I see is that machine learning can be really good for identifying what is weird, but not good for that final step, which is, why is it weird? And so I think here is where machine learning is going to be in partnership, not in competition with traditional statistics and with sort of good old-fashioned hard work. where maybe ML can sift through large quantities of data and point out some that need some further attention, but it's harder to figure out why they need further attention.
Thank you again. I think we have to move on. We're a little bit behind the schedule, so thank you again. And Doogesh, would you share the screen?
Yes.
Yes, our next speaker is Doogesh Kodi Ramanah from DARC, University of Copenhagen, who will talk about dynamical mass inference of galaxy clusters with machine learning. Please go ahead.
Thanks, Radek. So hi, everyone. First, thanks to the organizers for the invitation. So I will essentially cover the key highlights of our two complementary machine learning-based cluster mass estimators. And this is work done in collaboration with Radek Wojtak and Niki Arendse, who are both here today. So first, why do we need machine learning when we already have several classical mass estimators? Well, machine learning has some interesting advantages for this particular problem. So first, it allows us to optimize the information content of the galaxy cluster's dynamical phase space distribution. That is the distribution of galaxy positions and the line of sight velocities. And second, classical methods rely on some idealized assumptions, such as spherical symmetry or dynamical equilibrium, which may not hold in practice because of physical effects, such as dynamical substructures and cluster mergers. And third, it can deal with interloper galaxies to some reasonable extent, as we'll see later. Let me start with the neural flow mass estimator. So here I have a schematic of our neural flow model, which makes use of normalizing flows. Basically, this is a flexible framework for modeling arbitrary probability distributions. And in our case, we want to model the probability of the cluster mass given the 2D dynamical phase space distribution. And we train our model separately on the pure and contaminated catalogs from the recent paper by Matteo Maturi, which is derived from the multi-dog and body simulation. And the difference between these two catalogs is simply the presence of interloper galaxies. And I think Matteo will probably talk more about the mock generation later. And as a pre-processing step, we use a Gaussian KDE to produce a smooth phase space mapping of the 2D phase space distribution. And this was inspired by Matthew's paper. So the use of this normalized KDE representation makes the network more robust to galaxy selection effects. And you can ask me more about this later. Now let's look at the performance of our model for both the pure and the contaminated catalogs. So essentially, we plot the truth against the predictions, and we see whether our model can recover the ground truth masses, which is the case here for both the pure and the contaminated catalogs. So in the top panel, I'm showing the mean and the 1 and 2 sigma regions, while the dashed line in the bottom panels are showing the residual scatter epsilon. And this is basically the difference between the network point predictions and the ground truth. And the main difference between the performance on the pure and contaminated data sets is a larger residual scatter and correspondingly larger model uncertainties. And in terms of the residual scatter, the performance of our network is roughly a factor of 4 improvement over the M-sigma relation, which is rather promising. And to quantify the precision of our mass estimators, we follow the approach from the Galaxy Cluster Mass Comparison Project, whereby we fit this model to the scatter in the point estimates. And here we quantify the precision in terms of the richness dependent and independent components. And here richness simply means the number of galaxies per cluster. And one way we can interpret this is that sigma 0 describes the systematic error, while sigma n describes the the statistical error. So in the absence of systematics, then the total scatter is given by the statistical error due to Poisson noise. And here we can see that our neural flow mass estimator, as indicated by the gold stars, does pretty well in comparison to more traditional mass estimators. And the difference between the pure and contaminated cases is basically the presence of interlopers, which results in a higher systematic error. And next, to interpret the performance of our neural flow model, we derive the so-called saliency maps for 3 individual clusters in different mass regimes. And these saliency maps, which are shown here in the bottom row, basically illustrate the informative regions in the input 2D phase space maps, which are shown here in the top row. And the regions in red are the ones that contribute significantly to the mass estimate. And as expected, these are the dense structures associated with the main central cluster. And interestingly, the blue regions, which are further away from the central cluster and which are likely to correspond to interlopers, are also taken into account by the network. So this shows that the network has learned to deal with interlopers to a reasonable extent, which is rather interesting. And finally, we applied the trained network to spectroscopic observations of a handful of real galaxy clusters, such as Coma and the Lansing cluster A1689. Basically, we wanted to see whether we can recover well-established masses of some nearby clusters, which is the case, as can be seen here by plotting our predictions against their respective literature values. So in short, this neural flow mass estimator is looking rather promising. I will now move on to the simulation-based inference project. So this is a conceptually different way of estimating network uncertainties, but is of course complementary to the neural flow approach that we have just seen. And for this next project, we wanted to exploit the full 3D projected phase space distribution. So now we use both the X and Y positions, galaxy positions in the sky, along with the line of sight velocities. And this results in 3D KDE maps. So the underlying motivation here is to provide a better separation between members and interlopers by adding extra information from the position angle. And here we want to generate a mock SDSS catalog. So we need galaxies, and we have used a semi-analytical model of galaxy formation along with the multi-dark Planck simulation. And we basically picked the option that produces the most realistic distribution of galaxies. And then we have used SDSS flux limits to produce a cluster catalog that is as realistic as possible. And here we have a schematic of our CNN architecture. Basically, it takes as input the 3D KDE maps and extracts the informative features to ultimately produce a point estimate. But the idea here is to use this 3D CNN within a simulation-based inference framework in order to quantify the uncertainties on the network mass estimates. But I won't have time to cover all the details of this implementation here. So let's look at the performance of our network on our test set. And as before, we are plotting the ground truth against the predictions. And we're also showing the residual scatter epsilon in the bottom panel here. And the first thing that we note is that the network has a tendency to overestimate the masses for clusters in the low mass regime. And essentially, it's due to the presence of interlopers, as we'll see on the next slide. But the good thing is that this bias is taken into account using simulation-based inference. And we see that the network assigns larger uncertainties to these low mass clusters. This is one of the main advantages of using this framework. And next, we wanted to visualize the interloper contamination. So first, we identified the interlopers in each cluster as galaxies which are outside their virial radius. And then we make a scatter plot of truth against predictions with the markers colored according to the mass ratio of the interloper to the original cluster. And this size of the markers is given by the inverse distance between the clusters in phase space. And note that the color bar here is in log scale. So this mass ratio goes up to a factor of 20 for the most contaminated clusters. So essentially, this illustrates the overwhelming interloper contamination in the individual clusters in the test set. And as expected, the distance between the original and the interloper clusters is another factor that renders this mass estimation even more challenging. And in a sense, this contamination results in an overestimation for low mass clusters but this is accounted for using simulation-based inference. Now let's look at the improvement gained when working at the level of 3D phase space rather than 1D or 2D. And for comparison, we're showing the 1D and 2D results from Matthew's paper, and we are also using the same mock catalog. So the CNN1D uses information only from the line of sight velocities, while the 2D counterpart additionally uses the information from the projected radial distance, while our 3D version uses the full projected positions on the sky and the line of sight velocities. And here we're showing the residual scatter epsilon. Basically, we're showing the mean and the 1 and 2 sigma regions. So we see a clear improvement in the precision of the point mass estimates as we go from 1D to 3D. And this really justifies the use of the 3D CNN. We repeated the precision analysis from before, but now we illustrate only the recent machine learning methods. And as with the previous figure, we see the progressive improvement in the precision of CNN models when we move from 1D to 3D. And for comparison, I'm also showing these two horizontal lines for the Poisson-like scatter for richness-based and velocity dispersion-based methods. So in summary, this CNN 3D model is working quite well. We then applied the trained CNN to galaxy clusters from the SDSS main sample, and we used the Galway catalog from the paper by Abdullah et al., where they also provide dynamical mass estimates using a virial mass estimator. And on the left, we have a qualitative comparison between our predictions and those obtained using the Galway estimator. And on the right, we have the normalized 1D PDF of the difference between the two sets of predictions. And we have a roughly a normalized Gaussian distribution, which shows the overall consistency of our results with those obtained using Galway. We also used our SDSS mass estimates to perform a preliminary reconstruction of the mass function. We find that we recover the theoretical mass function for Planck lambda CDM cosmology roughly down to the mass completeness limit, which is an interesting result. And here's a summary of the key aspects of our two machine learning-based mass estimators. So the main thing is that we gain quite a bit in terms of precision by working at the level of the 3D phase space. And we have shown that by using realistic mock catalogs, we can recover the theoretical mass function down to the mass completeness limit. And in terms of future work, the next logical step would be to use our two mass estimators to infer cosmological constraints from SDSS cluster abundance. But this would, of course, require further thought, in particular concerning galaxy selection effects, to be able to do this rigorously. But it would be interesting to do this jointly with the recent variational inference approach that Matthew will talk about later. And then we'll have three complementary ways of quantifying uncertainties on the neural network predictions. I'll stop here. Thank you very much. And let me know if you have any questions.
Thank you, Doogesh. Time for one, maybe two questions. Maybe let's start with Sungwook.
Thank you for your talk. So I have actually two questions, but probably the first one. So in your CNN 3D method, so you used the two projected direction and one line of sight direction.
Yes.
But those line of sight direction is quite different from the two projection directions. So maybe just applying the 3D CNN method might have some imbalance between axes, or so. Do you have any idea of whether it doesn't matter at all, or it'll be good if we can apply some modification of the 3D CNN?
I'm not sure I completely understand the question. So you say that you're saying that.
So okay, so let me say it this way. So here, so X pros and Y pros and V loss, all of the three axes can be regarded as a spatial dimension, but VLOS include the redshift space distortion. So that makes the huge difference between the V loss and the other two axes. So probably that may affect when you just apply the 3D CNN. I'm not sure, but probably it's good to think about just a little bit about that.
Yeah, I'm not sure that would be an issue for the 3D CNN.
Okay.
Okay, maybe one more quick question, Andrea.
Yeah, thanks, Radik. Beautiful work, Doogesh. I just want to know how far are you from estimating mass profiles and velocity isotropy profiles? Because we're using project phase space with a traditional MAMPOS method to try to learn about mass profiles by starting with basically with models. So how far are you from getting there?
I think that that would be interesting future investigation, but so far we have not thought about that. But yeah, I think this would be an interesting possibility to explore with these two methods. Yeah, thanks.
Thank you. Yeah, let's move on to the next talk. So Sungwook, would you share the screen?
Okay, so can you see my screen?
Yes, we can see. So so here's the next speaker, Sungwook Hong from
Korea Astronomy and Space
Korea
Science
Astronomy and Space Science Institute, of course. Yes. So please, the floor is yours.
Okay, so thank you for having an opportunity to giving us a chance to talk with this wonderful workshop. So my name is Sungwook Hong, and my talk title is the weak lensing mass map reconstruction of merging clusters with convolutional neural network. And my collaborators are Dr. Ntampaka and Professor Dong-Soo Park at University of Seoul, and Professor James Ji and Mr. Sang-Jun Cha at Yonsei University. Okay, so the main topic here is the mass map from the weak gravitational lensing. So most of us knows well about the weak gravitational lensing, so I will go through this very quick. So the weak gravitational lensing can be used to understand the evolution of the emerging clusters, and also it can be used to constrain cosmological parameters. One caveat here is that we don't know the original shape of the single background galaxy. So if we measure the shape of the source galaxies, we do not know how much part of it comes from the intrinsic shape and how much coming from the weak gravitational lensing. So to marginalize that effect, we need statistics of background galaxies, not only a single galaxy, but with several galaxies around certain region to measure the shape distortion that is affected from the weak gravitational lensing. So here is some of the classical method to the mass map reconstruction from the weak gravitational lensing. So when you measure the background background galaxies around at the behind of the certain galaxy clusters, then you can measure these kind of the shear map. So each of the line here is the average of the shape of the background galaxies. So they're the average of here and this region and this region. So each of these points can be regarded as the field of the shear vector. And this has this kind of two-dimensional direction, and this can be decomposed into two parameters. One is the ellipticity and another is the rotational angle. Then by using the linear theory, one can calculate the so-called convergence. So that is the estimator of the dark matter distribution, projected dark matter distribution, by using this kind of linear theory. So this is some of the classical methods that can be discovered, made by Kaiser and Squire in 1993. So, and this is one of the example of the measurement of the mass map around the L-Gould cluster was done by Giero 2014, from this shear map to this convergence map. So these were the linear theory are lovely, but there is some of the limitation. So one very well-known limitation is so-called mass shear degeneracy. That is, for the same set of the shear field, where there are multiple values of the convergence field is possible. For example, if one calculate the convergence field kappa from a given set of the shear field, and from the exactly same shear field, if you just multiply a certain constant lambda, to the given convergence field plus 1 minus lambda, that gives the exactly same shear field. So one cannot distinguish which lambda is the true value if you only see the shear vectors. Of course, people have developed the way to marginalize this meshy degeneracy. For example, by the far ends from the cluster center, then one can assume the kappa value should be 0 or something like that. But anyway, intrinsically, so if you use the linear theory, then meshy degeneracies are there. Or, as I said before, the shear vector measurement cannot be done by measuring only one galaxy. What you need to the average over a certain range. But the way of the averaging may change the calculation of the kappa. For example, if one has the same set of the background galaxies, but depending on how largely you average to measure the shear vector, you can get this kind of map, convergence map, or this kind of convergence map, which are quite different. So these are some of the intrinsic limitation of the classical methods. So instead of doing this kind of set, we would like to propose the new method based on the convolutional neural network. So here are the basic the framework of our methods. So we will apply the two of the shear vector E1 and E2, and also the intrinsic measurement error factor delta E as the 3 layers of the input in 3 channels of the input layer. And then we would like to get the convolution, the convergence field as an output. So here, most of the processes are done by using the convolution and transpose convolution. And as many of us we know, so the convolution is something like how to change the image by applying the finite set of the kernel. So if you are familiar with the image transformation, such as for the Photoshop or GIMP, then there are many ways to change the image by using some sort of filters, such as Gaussian blurs and sharpening the image or making only the boundaries of the image. Well, most of those kind of simple filters are defined by this kind of small kernels. So similar to that, but these kind of kernels can change the shape of the images. These kind of the convolution process tries to grab some of the features from the given set. Not only doing the convolution and transpose convolution, we also sometimes multiply the channels, the layers a few steps before that. This is what we did to retain the small scale structures. Otherwise, if we only do this kind of thing, then we were worried about losing some of these small scale structures. To minimize that kind of loss, we applied this kind of multiplicity. At the end, so all of the deep learning is also the finding the sum of the minima. So in our case, we would like to find some optimal values of this kind of the kernel value, also some of the nonlinear stuff. So we define the loss function. Here, we define so-called the focal loss-like loss function, inspired by the focal loss, for example, linear or 2017. So this loss function is, if we see this part only, then this is just the usual mean squared error part between the prediction and truth convergence map. But we added these parts, so that is some of the factors related to the distribution of the truth value of the convergence map. We did this because in the actual convergence map, many of the pixels are having very low values of the convergence, while the cluster region, which we are interested in, has a higher value of the convergence, but the number of pixels are small. So there is some of the imbalance between the number of pixels for different values of the kappa. So in order to avoid that kind of too much bias onto the underdense region, so we apply this kind of additional weight for the loss function. Finally, if we only use the single the deep learning run, then we would not likely, we don't know whether our result is accidentally good or our method itself retains good results. So we apply the same method, but run 10 different times so that we can learn 10 different, slightly different set of the parameters. Also, we apply the input data augmentation. So for example, all of these are the field of view, then where we divided like this kind of thing, and where we patched something like that, we also apply the rotation and flips. So these are the training data sets. So we applied a massive NUS MOX convergence map and selected 7,000 field with a 32 arc-minute by 32 arc-minute field of view. And we used that as outputs. And we randomly generated source galaxies behind, so 25,000 galaxies per field. And we apply the intrinsic shape noise and also apply the measurement error, so that these will be given by inputs. So we divided the 7,000 field as these kind of training and validation and testing set. So these are the visual inspection of the results. So this is the truth map, and this is from the classical method. And this is from our CNN method. So, and also these are some of the normalized maps. So as we can see, our method gives the better positioner, but also the overall structures, while the classical method the low contrast and sometimes give even the wrong position of the cursor peak. So more quantitatively, we apply the 2D probability with the joint probability relation between the truth value and the prediction. So this is coming from the classical method, and this is our method. So why classical methods are highly biased and having usually relatively low values of convergence, where our method is slightly better. And if we go to the cluster mass, defined by the sum of the convergence map within the 1.92 arc minutes around the cluster center, then our method gives the much better agreement with the truth value rather than the classical method. Also, the peak position accuracy is quite better. So if we compare the peak position difference between the classical method and CNN method, and the CNN method gave mostly the better result, even though the classical method gave the wrong position accuracy. We also apply sometimes the bright galaxies appear to the field of view, and that could distract the measurement of the weak lensing map. So we tested those kind of possibilities, so that we sometimes mask some of the regions by assuming there is a bright star. So here, these values are our previous deep learning method result, and this is after applying the mask. So of course, but because of the existence of the mask, so the overall performance becomes lower. But even that, this was better or comparable to the classical method without applying the star masking. Finally, we applied to the real data, so-called Algorithm clusters. So this is the classical reconstruction, and this is our method. So here, the range of the convergence value matches with the expectation, and also it gives the better reconstruction of the two density here. And also it does not have some spurious small scale fluctuation occurs in the classical method. But we need to worry about, we need to be cautious, because our method was not optimized for the HST data that we applied here. The optimized data was different set. So this is just only for the demonstration, but not too scientific. So here is the conclusion. So deep learning can reconstruct the projected mass map from the weak lensing, and it has potential that were better reconstruction than the classical method. So mostly this is because the deep learning has a potential to dealing with the non-linearity behind the weak lensing map reconstruction between the convergence map and shear field. So this is all of my talk, and thank you for listening.
Thank you for a very interesting talk. Time for one question. Matteo, please go ahead.
Hi, nice talk. Just a very brief question. In one of your reconstructions, there is a large structures in the top left panel that do not appear. Is that because it's close to the border and you're where there is the map? You went through the slide.
This one?
Yes. So in the top left corner in the simulation, where there is the truth, there is quite a large structure, and this doesn't quite appear in the other image, in your reconstruction. Is that because it's next to the border and because you're flipping the images, let's say that the outskirts are not well reproduced, or is there some other reason for that?
So your question is, though, there is some of the large scale structures, something like this and this, but what it does not show in here.
Yeah.
So I think that is still what there is some of the room for improvement. So, but if we see the classical method, for example, even this does not fully reconstruct this thing. So probably that is some of the partly intrinsic problem and partly our method has some of the room for improvement.
But it's the sensitivity is uniform across the whole field.
In the boundary, there might be a little bit less, but still, yeah.
Thanks.
Okay, thank you. I think we shall move on. So let's switch to the next speaker. Daniel, would you share the screen?
Yes, sure.
Yeah, the next speaker is Daniel de Andres Hernandez from the Autonomous University of Madrid, who is going to talk about deep learning approach to infer galaxy cluster masses in Planck-Compton parameter maps. Please go ahead.
Hello, everyone. Can you hear me clear?
Yes.
Can you see my presentation?
Yes, all is clear. Okay,
great. So I present myself again. I'm Daniel de Andres. I am a PhD student working at Universidad Autónoma de Madrid, and I'm under the supervision of Gustavo Yepes. And I'm going to talk about deep learning approach to infer galaxy cluster masses in Planck-Compton parameter maps. I am a member of the 300 project, which is a state-of-the-art simulation aiming to simulate galaxy clusters. And these are my collaborators. We have a machine learning group in this project, and we're also working with the help of a company which is called Unanova, and they're helping us develop the state-of-the-art artificial intelligence algorithms. Okay, I'm going to tell you briefly about a brief introduction about this topic. So as you know, galaxy clusters are the biggest gravitational bound objects in the universe, and then they can be observed through the SZ effect. So in the microwave background. The Planck collaboration collected a full sky survey of these SZ clusters, and they estimated their mass through integrating this parameter through an aperture. So they estimated their masses through a scaling relation. And however, the way they estimated their masses used the hydrostatic equilibrium hypothesis and is supposed to be biased low. So we aim to address this issue by training a convolutional neural network on a large catalog of almost 200,000 simulated clusters that are very similar to the Planck SZ maps. So they have the same angular resolution and noise levels. And these clusters are simulated using the 300 project. So this approach is, as other people commented, is nice because we don't assume any a priori symmetry. So we aim to find a mapping between the simulated SZ maps to infer the 3D dynamical mass of the clusters. First, I'm going to describe how our dataset is created. Okay, our dataset is based on extracting almost 7,000 different clusters from the 324 regions of the 300 simulation. Furthermore, we use 27 different projections of every single cluster, amounting to a total of almost 200,000 maps. We use this selection, we use a selection of clusters to uncover the full Planck PSE2 catalog, so that our simulated data, which are blue points, need to cover the observational data, of course. Furthermore, we have trained for CNN different models for different redshift beams. This has been done in order to improve our predictions. So we have nearby clusters, another redshift beams, and then a redshift from 0.4 to 1. Well, this is how our data looks like. First, we have let's say the clean mock data. It is the simulated data with the same angular resolution, which is 1.7 arcmin as the real Planck data, but without introducing the simulated noise. So as you can see, we have clusters from different masses and different redshifts. Then from this mock clean data, we have simulated the noise, which is the instrumental noise from the Planck catalog. So we statistically simulate the noise with the same power spectrum of the Planck maps. And as you can see, they're very similar as the observed real Planck data. Okay. Then I'm going to explain a little bit about the architecture that we have used. So we use a version of the VGG network, but this architecture has been successfully used in simulated data by Michel and Jan in previous studies. And this architecture is based on convolutional and pooling layers to extract the features of the maps. And then once these features are extracted, we simply train a dense block of neurons to perform a regression between these extracted features and the total mass of the clusters. So this algorithm is trained in a supervised way. And once this algorithm is trained on the simulation data, we simply apply it to infer the masses on the real Planck data, which is by construction really similar to the simulated data. Okay, using this data and this architecture, I'm going to show you what our results are. So first, I'm showing the results using the simulation data. Well, here in the y-axis, we have defined a quantity, which is the relative error. So it is a comparison between the predicted mass, the CNN mass, and the true mass, the mass from the simulation, the 3D dynamical mass. And in the x-axis, it is the CNN predicted mass. The black line shows the median, and the regions, the shaded regions, show the different percentiles of our data. As you can see, in this left panel, we show the prediction on our test set using the clean data. As you can see, the predictions are not biased. Let's say if you interpret this quantity as the bias, the prediction is not biased in the whole Planck mass range. And the scatter is of order 1%. And when we introduce the noise, what we simply are introducing, as far as this CNN model is concerned, we are not introducing any bias because the predictions are still not biased, but the scatter is greater than using the clean images. Now let's move on to the results on real data. In the left panel, we are still showing the results using mock Planck data, but instead of comparing the CNN data with the true D dynamical mass, we are simply comparing the CNN mass with respect to the SE mass. So the mass computed using the same Planck scaling relation. So from Arnaud et al. So if we compute using our simulated data, the SE mass in the same way as in the Planck collaboration did it, what we obtain is this result. So instead of having an unbiased prediction, what we find is that for the low mass range clusters, it looks like the MSC is overestimated in the sense that it has the same, so this bias is close to zero, so the predictions are unbiased, but when we move to the high mass range, we obtain a similar bias, which is compatible to the bias, the expected bias of the Planck masses, which is close to 0.2. And when we see these results on the real Planck data, we found a similar trend in the sense that for low mass clusters, the SC mass is overestimated, simply arguing that the SC mass might be overestimated, so we don't find the expected bias. It should be close to 0.2. So, and we simply have checked with different scaling relations and checked the interloop personal simulation, and this could be simply compatible with that the Planck scaling relation is not calibrating using the 300 simulation. So the calibration of the scaling relation is different. So indeed they use X-ray maps, and the calibration is different. So it is compatible of finding that the SC mass of the Planck prediction are of the same order than the CNN mass. If we interpret this result as a PDF, as a probability function distribution, so if we analyze these errors as a probability function distribution, what we find is that, as I told you before, from clean cluster and mock Planck clusters, and the fact of adding noise to the images simply increases the scatter of the predictions or of the errors. But if we compare the results with the SC mass instead of the 3D dynamical mass, what we find is that for the low mass range, or for all ranges, we have this kind of over prediction of the SC mass. And when we move to this region, which is the high mass clusters, what we find is that the result is compatible. It is close to 0.2. It is compatible to the expected bias of the Planck observation, which is close to 0.2. But the point here is that when we go to real Planck clusters, we obtain a similar result for all recipients. So the nearby clusters, which is represented by the blue line, when we go to the high mass range, we simply get rid of this overestimation of these clusters and we obtain a bias of 0.2. But however, for the long distant clusters, so the far away clusters of higher redshift, we obtain that the results is close to minus 0.1, and we still do not understand very well what this might be happening for these clusters. So now I'm going to tell you a brief summary about the ongoing machine learning projects within the 300 collaboration. Apart from simply inferring the one-dimensional, the scalar dynamical mass, we want to infer the total mass map, so the 2D mass map from mock observations. So instead of simply trying to infer the 1D mass, we want to solve the 2D problem, trying to infer the 2D mass from mock observations. We also want to infer dynamical state properties from mock observation as well, such as the dynamical state of the clusters, if the cluster is relaxed or it is unrelaxed. And also we are creating a catalog of variance properties from dark matter only Halo catalogs, so that this might be applied to construct a fast full-scale survey that might be useful for upcoming surveys. Well, the conclusions of this project is that we have managed to give an estimation of the total cluster mass without any assumption of any symmetry or any assumption of the dynamical state of the cluster. We found that the counterparameter might be overestimated for low mass clusters. And also, the results on the simulated data And the results of real data are slightly different, but nevertheless are statistically compatible and show an overall trend. The possible difference might be due to different physics modeled by the simulations, of course. I have to point out that we have tested our algorithm with the Gizmo run. So it is a different code for the simulation, which includes a different variant physics, and the results were consistent, so there were no different. So we find no significant difference between running the simulation with Gizmo or with Gadget X. Well, the point here is that hydrodynamical numerical simulation are an indispensable tool to provide the mock observation on which we can train our CNN architecture or any other machine learning algorithm. Okay, thank you for your time. Thank you for having me. Do you have any question?
Thank you for your wonderful talk. Time for question, one, maybe two questions. Sebastian, please go ahead.
Yeah, thank you. Very nice talk and very nice project. I guess I'm just curious. So on the one hand, you showed basically that the 300 simulation have more realistic clusters than other scaling relations you're compared to. So I think that's very good news. So my question is, how much better does your machine learning based mass estimation perform compared to if you had simply fit a, let's say, Y mass relation in a simulation and applied it to the data set? I mean, have you done like?
Yeah, I think, yeah, you can see it here. So if we compare, well, simply you use the machine learning. This is on the simulated data. Well, this is the result on noisy data. So you see that here the scatter is of 20%, right? And if we introduce them, well, the noisy HC estimation, because we compute this as if it were done in an experimental setup without knowing the true radius. So we introduce for the low mass range a lot of scatter here. So using this, well, I don't have here the number because I haven't compared this with the real 3D dynamical mass, but the scatter is higher than the CNN approach because we here increase the scatter by
okay, I missed that. So that's the comparison. Okay, yeah, so you say you gain like 50% in scatter or something.
Yeah.
Like that. Cool.
Yeah, and of course the scatter is greater for the low mass range. And if you use the CNN approach, the scatter is kind of constant for the whole mass range.
Okay, thanks. I hadn't made that connection. Thanks a lot.
Thank you.
So maybe very quick question, Ben.
Yeah.
Yeah. So the CNN masses are lower than the Planck masses at high redshift, and the CNN masses agree with the true masses at all redshifts. So is this just telling us that the evolution in the YM relation in the simulations is different from the one that's assumed in the R node?
Yeah, you see, yeah, it kind of agree with the whole redshift, but it looks like this red curve, which is corresponds to the high redshift, is different from them.
Yeah, well, I'd say, yeah, the blue peak is sort of towards the right, the green is in the middle, the red is towards the left. So you could test that directly to see what the evolution is you get from the YM relation in the 300 versus what's assumed.
Yeah,
similar evolution.
Yeah, that could be the point, that the evolution of the 300 simulation is not, let's say, the evolution that in the Planck measurement they supposed. But yeah, it looked like the evolution of the Y parameter of the gas density of the 300 simulation could be different from the Planck use. So this method could be applied to detect outliers in this sense. Yeah.
I'm sorry, I have to interrupt. We can continue on Slack, or maybe
Okay, I will be available on Slack. Thank you very much.
Yes, thanks a lot. And let's switch to Matthew Hall. Matthew, if you exactly. So the next speaker is Matthew Hall from Cornell University, and the talk on galaxy cluster masses from approximate Bayesian deep learning. Please go ahead.
Yeah, thank you all so much for having me. Hi, I'm Matt Ho. I'm a 5th year graduate student at CMU. I want to start by thanking all my collaborators listed here, and also graciously thank Doogesh for the references in my talk. A lot of the stuff I'm going to talk about today is similar to what Doogesh mentioned, so I'll try not to repeat too much information. But primarily, we're going to be talking about how you can apply deep learning to dynamical mass estimates and get very low recovered scatter. And I'm also going to introduce this idea called approximate Bayesian deep learning, which can be generically applied to a variety of different deep learning models to get uncertainties. Okay, so our story starts in 1933 with Fritz Zwicky, when he made the first inference of dark matter in the coma cluster. Right. This is like a fantastic starting point, I think, for dynamical masses, because it represents a historically significant application of the M-sigma relation, which everyone probably on this call knows by now is the relationship between the velocity dispersion of a galaxy cluster and its total system mass. And the nice thing about this relationship is you can derive it from first principles if you assume a number of things about your system. But the unfortunate part about it that I'm sure everyone recognizes is that it's not so simple. It turns out that direct application of the M-sigma leads to considerable scatter on mass estimates of galaxy clusters. And the reason for that is that there are a variety of known systematics which affect this measurement. I've listed some here with some references of people who've investigated these topics and tried to either account for or mitigate or quantify the impact these have on mass estimates. So these include like dynamical substructure, cluster triaxiality, and contamination of your sample. So effectively, when you select your galaxy sample in your cluster, which includes some interloping galaxies along the line of sight, which may not actually be gravitationally bound to your system. So each of these kind of introduces some amount of scatter to the system. But the primary concept that we want to use when we apply deep learning to this is that it turns out that a variety of these systematics are visible in dynamical phase space. So the classical representation of this is if you take all the galaxies in your galaxy cluster and you plot it with line of sight velocity on the x-axis and projected radial distance on the y-axis, you get the distribution of the cluster's galaxies in dynamical phase space. So the idea is that a variety of these systematics, like dynamical substructure here or interloping galaxies, appear as artifacts in these distributions. And historically, before complex interloper removal and algorithms were developed, people would remove these artifacts by eye, effectively. So we thought, if these systematics affect dynamical mass estimates and you can identify them by eye, why don't we try to get better eyes? Effectively saying, like, if there are a variety of image recognition tools on the market today, how can you apply these to improving or mitigating the effect of these systematics? So this is the general strategy: is we take these distributions of dynamical observables and we turn them into images using kernel density estimators, which also kind of normalizes them to selection effects and sample robustness and sample richness. And then we feed this to a convolutional neural network, which is effectively the gold standard in image recognition tools, and we output some mass estimate, right? So in general, deep learning models can seem a little bit scary, but really in this context, all we need to know about them is that they are effectively just very highly nonlinear functions with very nice gradients, right? So you put in some input and you get some output, and the relationship between them is nonlinear. But the nice thing about the gradients is that you can then use gradient descent to optimize this relationship given some training data, right? So this is what we did. We took this particular type of model, which is called a convolutional neural network, and we trained the relationship between these dynamical observables and mass estimates on a realistic mock catalog of galaxy clusters, which was primarily based on the multi-dark simulations and the universe machine galaxy labeling procedure. And these are the results that we got. We found that when evaluating this model on an independent test set from simulated clusters, the deep learning models applied to this dynamical information reduced the scatter of simple M-sigma measurements by up to a factor of 2.5. So that's what I'm showing here on the bottom right. I'm showing the logarithmic prediction residual of cluster mass across a variety of different true masses. And in red, I show the effective scatter of the M-sigma relation and our results in best model in blue. The other interesting result from this is that not only were we doing better than simple M sigma measurements, we were doing better than ideal M sigma measurements. So if we assumed that the M sigma predictions had perfect galaxy selection, which would be equivalent to saying that all of our interlocal removal schemes worked perfectly, we still improved the prediction scatter of ideal M sigma measurements by 30%, even when we gave the model the contaminated sample, which is a notable result. In addition to this, we also found that our model was had significantly reduced sensitivity to cluster richness, which was a result of the kernel density estimation. And also at the time, we were improving the training and inference time by up to 30%, 30 times what was initially the benchmark from other machine learning approaches. And I've shown on the right the plot that we've seen before in this conference, which show our results on the respective intrinsic and richness-based scatter relative to previous mass estimators at the time. Okay, so this is all great. This first paper, which was published in AppJ, was able to estimate point masses of all these galaxy clusters. But in order for this information to be useful to cosmology, we not only need point estimates, but we need uncertainties. So we're broadly trying to then characterize how can you take some given input like dynamical phase space information, throw it into a neural network and output some predictive posterior of cluster maps, right? And there are a variety of ways to do this, which are currently in the machine learning literature. And I've listed some here. Two of them were already discussed in this workshop by Doogesh. And the one that I'm primarily going to be talking about is this idea behind approximate Bayesian neural networks here. Deep learning models in general can seem a little bit intimidating, and it might not be initially intuitive of how you can get uncertainties out of these deep learning models. But deep learning models are just like regular models. You have some parameters which define your model, and you use training data to fit those parameters. And just like in a linear regression, if you use your training data to fit those parameters, there's going to be some uncertainty about all the different parameters that could exist. So if you want to do a full inference of a deep learning model, you need to marginalize over all of the uncertainties in all of the parameters in your model, right? So effectively, the training data that you have dictates some manifold of all the possible parameters you could have for your model. And in an ideal world, you would then marginalize over all of that uncertainty to produce an effective output posterior, right? So in the context of galaxy cluster mass estimation, you'd effectively say that to get the mass posterior, given some dynamical phase space information, some assumed neural network architecture, and some training data, you would marginalize over all the weights and biases associated with the parameters in your deep neural network. And those familiar with machine learning should recognize the fact that this is impossible to do for deep neural networks because they have hundreds of thousands of parameters, each of which can have very complex uncertainty manifolds. So instead, the point behind approximate Bayesian neural networks is to say, we assume some variational distribution over this parameter uncertainty, which greatly simplifies this calculation. So in a paper presented by Gal and Gaurami in 2016, they presented this idea behind dropout variational inference, which basically assumes a Bernoulli variational distribution over the uncertainty of the parameters in your model, right? So you effectively say that they can either have their value or zero with some randomness. And in order to produce inference on this type of model, you would effectively take your fully trained neural network and cut out some of the weights and randomly drop out these weights and output some mass prediction. And you do this like 100 times and marginalize over all the different possible outputs. And this gives you some sort of estimate of posterior uncertainty. So this is what we did. We took our existing model and applied these techniques. And instead of trying to reduce scatter, we were instead trying to characterize the scatter to the best of our ability. And we found that the model posteriors that these models produced were consistent with true masses and were Gaussian, even when we gave the output posteriors very high flexibility. And for middle range mass clusters, we were able to recover the 64th and 90th percentile confidence intervals to within 1%, which is was very good for us. However, we did notice that there were slight biases at the edges of our training set, which is something that we need to account for in the future. So we've now moved on from the pure theory and expanded it to observation. So we've applied this model to the Coma galaxy cluster. And in an upcoming paper, which we've submitted to Nature Astronomy, we constrained the mass of the Coma cluster, which started the story back in 1933. And we find that our model predictions are very consistent with previous estimates, with very strong consistency with estimates within the past 10 years. So one other thing I want to mention just before we end is that the purpose of using deep learning models here is that they're very useful for very complex data. And we've seen both in this workshop and in the literature that you can apply deep learning models to a variety of different wavelength measurements of galaxy clusters. So an interesting result would be if we could take all of these wavelengths of galaxy clusters, could we constrain more than just the galaxy cluster total mass? Basically saying that if we took measurements of galaxy clusters from a variety of different wavelengths, could we constrain the cluster mass distribution? Because this would be very useful for validating lambda CDM. So this is something that we're working on, but one thing that we're limited on is the availability of nice large hydrosims and mock simulated observables for clusters in these hydrosims. So I'd love to talk to more people about this if you're an expert on creating mock observations in these wavelengths. Okay, and then I will end with just my conclusion slide, and I'm happy to take any questions. Thank you.
Thank you so much. Perfect timing. Time for questions. I can see Matteo.
So you are going to you're planning to basically join multi-wavelength observations together. How do you think you can manage biases and this sort of uncertainties?
Yes. So I think, as was mentioned previously in this workshop, the performance of these models is limited by how well we can model the observables in the simulation, right? And they will always be limited by that extent. If there are inherent biases in the simulated observables, our method would be equivalent to the best possible methods using traditional techniques. So effectively, this is something that we're thinking about, both how to accurately model these in simulation and also how to detect the presence of biases in our predictions. But it's something that's still kind of an unopened question at the moment.
So sorry, let me rephrase. So you showed how you can make an estimation of your uncertainties, right?
Mm-hmm.
So could you detect tensions between the subsets, for instance, or I don't know, something like that?
Yes. So you could say, for example, you could train a neural network just on one wavelength observation, and then you could train a neural network on a variety of different wavelength observations, right? If there's tension between the predictions from one wavelength and the variety of wavelengths, that would suggest that either the single wavelengths predictions are biased, or there is something weird happening on the full multi-wavelength thing. So yes, you can kind of permutatively investigate what inputs you give your model, and perhaps investigate tensions between these different wavelengths observables.
Okay, thanks.
I can see Gary. Please go ahead.
So very nice talk, Matt. Very nice work. I'm very impressed, as you know. And so I have a detailed question and then a general comment. So my detailed question is, I'm curious if you compared your Coma analysis to that of Doogesh. Of course, we have to talk about mass of the same aperture. And my general comment is, it's all very nice to get masses for clusters. And I assume that you're talking about also surveys, spectroscopy being expensive. There's a lot of surveys like Euclid will be mainly based on photometry, but I guess you could try, the neural network might help nevertheless. But I think that in the end, we might need a neural network to detect the damn clusters.
Yes. Yeah. I think, so my only hesitation towards using neural networks to detect clusters is just if your goal is then to down the line model selection effects, right? Modeling the selection effects of a deep learning model will be complicated, right? Because it's this kind of black box thing. I think it would not be a bad idea to like use deep learning to say, oh, look in this region of space, and then use traditional methods to find centers and such. But I think that is a interesting project down the line. And the other thing,
you could imagine a deep learning method that will identify clusters or not. Then you can ask yourself, you can do it many times.
Mm-hmm.
Okay, there's different training, I don't know. And then assign a probability that a cluster is a cluster and that a galaxy belongs to a cluster. And then you can do it probabilistically with ABC or another way of doing that, or just by doing many simulations.
Yes.
Many CNNs, sorry.
Yes. And also just to answer your other question, yes, right here, this is Doogesh's very nice coma mass estimate, and we've shown that it is consistent with our predicted models, our predictions of the coma cluster.
So our dispersion kurtosis was a little bit higher by 0.1 dex. Okay, back in 2003. Okay. I'm not surprised.
Okay, I'm sorry I have to interrupt you though. I think we can continue at the end of the day in Europe. So thank you, Matt, again for a wonderful talk. And let's switch to Sheng-Chieh Lin. I hope that I pronounce your name correctly.
Yes.
Excellent. Would you share your screen?
Yes.
The presentation, yeah.
Okay.
So.
All right, can you see the screen?
Yeah, Sheng-Chieh Lin from University of Kentucky, and you are going to talk about a transfer learning model to estimate cluster masses from SDSS multiband images. Please
yes. Okay, thank you. So hi everyone, I'm Sheng-Chieh Lin. I'm a second year student here from Kentucky. And today I'm going to present our work on estimating cluster mass using a machine learning model. And this work is done together with my collaborators, Yuan Su, and people listed down here. So I believe that this is the third day of our meeting, and there's no need to emphasize how important is the estimating cluster masses. But in most cases, we still need to infer cluster mass through observable properties of galaxy clusters, scaling relations, and these mass proxies have their own pros and cons. And for example, for the product of mass gas spectral temperature YX from X-ray surveys, it provides an excellent mass proxy with low scatter. And for SC, we can obtain the mass of really high Z clusters. But in general, for this measurement, they are less available due to the expensive and time-consuming observations. On the other hand, galaxy cluster can be efficiently found in optical surveys. So we would like to explore the possibility of combining optical data with measurement so that we can bring the advantages of these observations all together. And this is achievable actually through, because for machine learning algorithms, it is really good at approximate, the nonlinear mappings between the outputs and input. In our case, we use CNN, convolutional neural network, because to train on the imaging data. Okay, so excuse me. In order to train our model, we prepare our sample from the RedMapper cluster catalog, which contains 25,000. After cross-matching with SC and X-ray catalogs, we find there's only 15 clusters with those measurements. And in fact, this measurement is extremely insufficient to train a deep learning model. On this issue, we apply a so-called semi-supervised learning, and this process is as following. We first train our model on the clusters without X-ray or SC measurement, and this training gives us a set of weights that present a good that could represent the important features of these clusters, and then we use this weight to increase the actual training on the 1515 clusters, so that we can overcome this extremely insufficient number of clusters for training. And here is our algorithm. It contains two neural networks. The first one is the feature extractor performed on the classification task, and the second network performed the regression task, which is estimating cluster masses. So for the feature extractor, it takes the SDSS multiband images as inputs and to predict the photometric band of these images. So through this training, we expect the feature extractor to obtain meaningful features that could represent the galaxies in color colored space, and also their photometry information and the differences between each color bands. And we output the feature vectors or feature maps before fully connected layers and use it as input to train our mass estimator. Additionally, we provide the network, the mass estimator, the information about redshifts in order to help it improve its performance. So the reason we adopt this complicated design is that for traditional convolutional neural network, for example, for the residual network ResNet 18, it is impossible for it to achieve such goal, which is directly estimate the cluster masses from images. Moreover, it is extremely versatile that you can attach different kinds of regression network after the feature extractor and perform on different tasks to, for example, estimate different observable properties of galaxy clusters. And here is our result for band classifications. We reach an accuracy of 92%. This indicates that the feature extractor actually acquires the photometry and also learns those meaningful features that represent the galaxy's distribution in a hyperdimensional color-colored space. And on the left here, we showed our main results, the predicted cluster masses as a function of ground. And here we also plot compare our results with the richness, and the horizontal dashed dotted line show the richness cuts applied in the original RedMapper catalog. And it is obviously that our result is comparable to the RedMapper richness. And we also find there's certain overestimated low mass clusters in our predictions. But overall, we achieve a pretty good result here. And statistically, our mean absolute error is 0.23, and which is at the same level of accuracy of. And here we show two statistics as a function of cluster mass and redshift. So the first statistic is the mean, and the second one is the differences between the prediction and the ground truth. So on the left here, we find that indeed we find at low mass scales, RedMapper both over the masses, and this is highly due to the richness cut applied in the RedMapper catalog. And for our cases, it is likely due to that the low mass clusters in general, they are harder to train because of the projection effect due to certain galaxy interloopers. And on the right here, we show the redshift dependence, and surprisingly, we find that our result has a larger scatter at all scale of redshift compared to RedMapper. Could indicate that we might need certain more careful treatment to input redshift information into the networks. And to train for training a machine learning model, not just about getting a result, but also we are curious about getting a we are also curious about how our model makes prediction, and this could be understood through certain interpretation methods. So here we adopt two interpretation methods. The first one is so-called the integrated gradient method to both networks, the feature extractor and the mass estimator. But for mass estimator, we also adopt another method called class activation mapping. This is because that the obtained integrated gradient maps of mass estimator has different dimensions compared to the original images. And to make a fair comparison, we need to find a way to deproject the IG maps back to the original images. And here is our results on interpretations. So the upper row shows the training images, and the middle row shows you the integrated gradient results from the feature extractor, and the lower row shows you the integrated results using the CAM to deproject back to the original image from the mass estimator. So and also the red open circle here, the red mapper classified cluster members. So we find several interesting features here. First is that we observe that bright objects they gain more attention from our network, and such as the BCG at the center of the images, because they have higher brightness background. And also we find that the bright stars also gain much more attention from the network. And another interesting feature is that we find that the background noise is typically ignored by the feature extractor, and those bad pixels are also ignored. And in general, for the results from the CAM plus IG more abstract, and because the inputs of these mass estimator are layer of feature extractor, that these feature maps are actually more abstract and conceptual and make it really hard to interpret. So in summary, we adopt the semi-supervised transfer learning to predict the cluster mass from optical data. Only using the real data, we do not pre-train our and we stress that performance can be scaled up with larger training data, especially for those at lower mass cluster, for those lower numbers. And this is accessible in the near future through, for example, Rubin Observatory. And we definitely need a more careful treatment to take those bright stars into account, since they can greatly distract the feature extractor from searching the galaxies. And in the future, we would like to include the Bayesian inference, because right now what we are doing is the point estimate, and we would like to obtain certain more robust results with the uncertainty measurement. And this is all for my talk today. And thank you for listening.
Thank you so much. Time for questions. You can also write on chat if you are too shy. So maybe a quick question from me. How do you deal with the uncertainties on your cluster mass estimate?
Yeah, so what you can use is so-called variation inference, that you can sort of, instead of giving its weight as a fixed number, you can provide it So the weights in the neural network, you can make it from a single value to a certain distribution. So every time forward propagation, the weights will be determined through certain, for example, the normal distribution, and so that you can estimate the uncertainty not only from the data but also the model itself.
Thank you. There is one more question I can see. Yuan.
Hi, Sheng-Chieh. So I was wondering, like, you saw that the masses you made from images directly is pretty close to the red mapper mass indicators, although still slightly worse. So I was wondering if you have thought about like how to incorporate like catalog level of information, like what red mapper did in this kind of methods.
Yes, we believe that include catalog would provide can improve the performance. For example, if we only include the Galaxy catalog, our network might be able to deal with the bright star as well, like automatically, and make it easier to search for these galaxies.
Okay, I can see more questions. I think we shall finish the first part here. So thank you to all speakers. Wonderful talks. And I guess we are switching right away to poster flash talks. Anna, is Anna around?
Hi, no, Anna is not around. Bruno, I think you're muted.
Yes, I was muted, sorry. So do you see my screen now?
Yes.
Yes, we do.
Yeah.
But not on full screen mode.
Yes, not yet, sorry. How do I do that now? Yes, okay. So the first flash talk, sorry, so let's go ahead with this flash talk. Oh, I don't know what's moving to the next one. Is from Miriam Ramos-Serra. Go ahead.
Thanks, Bruno. So thanks everyone for attending this flash talk. So this poster that you can find in the webpage is basically comparing the properties from an X-ray selected cluster sample with a shear selected sample. And this work is in the framework of the eROSITA mini survey called IFEDS that you might have heard about it, and comparing with the shear selected sample obtained with the HSC recently published by Ugur at the beginning of this year. So in summary, the main results that we obtain is that 85% of the shear selected clusters have an X-ray counterpart in the IFEDS, which is really nice. 43% of these shear selected clusters lie in superclusters. And what is really interesting for us and the results that we found is that the dynamical state and the emergent fraction between the two samples is not different from each other. The luminosity, the polometric luminosity mass relation is also consistent between the two samples. And we also don't find a significant population of X-ray undiluminous clusters. So the shear selected clusters that do not have an X-ray counterparts in IFEDS are basically below the detection limit of the IFEDS. So if you have questions, please contact me and I will be very happy to discuss with you.
Thank you very much, Miriam. Next talk is from Lia Durava.
Yes, so hi everyone, my name is Lia Durava. I'm a PhD student at USP. I'm presenting preliminary results of galaxy cluster detection obtained with the cluster finder PZ-Wave in comparison to Amico and Ramanah tessellation. We're using the photometric data from the mini-JPass as a test for the upcoming wide field survey. In this slide, I'm presenting figure 2 of the poster, which shows the matching results between optical and Aegis X-ray catalog, displaying the mass distribution along the redshift range. So PZ-Wave is able to recover a galaxy group with mass of 2.4 10 to 13 solar masses at redshift 0.74. The analysis highlights the quality of the mini-JPass data and the potential of the survey to detect clusters down to the galaxy group scale with high redshift accuracy. That's it. Thank you.
Thank you very much. Yeah. Next talk from Michel Aguena.
Yeah, hi. My name is Michel Aguena. I'm a postdoc at the Particle Physics Laboratory of Annecy in France. And I'm presenting a poster on the clusters detected using the WASP cluster finder, which is an optical cluster finder that was applied to the dark energy survey. And in this case, we're applying this cluster finder on the DC2 simulation of LSST. And the interesting thing is that because it's a simulation, we have more control of all the observational aspects, and we try to evaluate the impact of having these optical effects, such as the magnitude, the observed magnitudes, and on the redshift, going from true redshift to Gaussian redshift, and the photosys. And we see the impact of all these different cases on the cluster detection and on the determination of the richness, which is our max proxy. So if you're interested, please check on the poster. Thank you.
Thank you, Michel. Next talk from Shenming Fu.
Oh, hi. My name is Shenming Fu. I was a PhD student at Brown, and I also started my postdoc at Lower Lab. So the local volume computer class survey measures the dark matter distribution and the galaxy population in about 100 low redshift and X-ray luminous clusters using the dark energy camera. So the depth reaches about LST year 1 to year 2. Until now, about half of data have been taken, and the survey will finish before the beginning of LST. Some preliminary results will be published soon. So we mainly use LST science pipeline to process data and then use our own pipeline to analyze the data. The figure here is showing the comparison among mass signal noise maps, X-ray maps, and optical image in the cluster ABLE 3911 field. So if you're interested, please come to the post-session and let me know if you have any questions. Thank you.
Thank you very much. Next talk is from Pradyumna Sadhu.
Hello, everyone. I am Pradyumna, an undergraduate student from IIT Hyderabad. So in 2016, Mega and others observed a radial axis relation, which is in rotationally supported galaxies. And this is a strong correlation with very low scatter observed between the radial acceleration inferred from the dynamics and the radial acceleration which is inferred from the observed baryons. On one hand, we have the lambda CDM, where we have to invoke complex phenomena like baryonic feedback to explain this. On the other hand, we have MOND, which is the modified Newtonian dynamics, which can explain this very trivially. And though we know that MOND does not hold in galaxy clusters, it would actually be interesting to check if the radial acceleration relation still holds in clusters. And this is important because with this, we can actually test lambda CDM and other theories which can reproduce RAR in galaxies. And we look at 3 X-ray selected samples. One is from the XCOP project, and 2 other samples are based on Chandra and Rosat observations. And we also try to redo the analysis for high flux samples. And for this analysis, we test whether the acceleration scale, the scatter, and the best fit RAR parameters are still the same as that of the galaxies. And for the punchline, do visit our poster. And also as an advertisement, I'll be applying to grad school this year. Thank you.
Thank you. Thank you. Next talk from Kamal Bora.
Yeah. Hello, I am Kamal, a PhD student at IIT Hyderabad, and I will talk about the variation of fine structure constant and the validity of cosmic distance duality relation. So the first motivation of searching variation alpha comes from the Hubble tension between the low redshift and high redshift probes, which could play a role, although minor, in resolving the Hubble tension. And the another motivation comes from a claimed variation of alpha from quasar absorption system with the Keck and VLT telescopes. So the first test for the variation of alpha using galaxy cluster as the observation was implemented by Gurley. This work follows the similar outline as Gurley. So we used 58 SZ clusters selected by South Pole Telescope, as discussed in yesterday talk by Lindsay and Sebastian, along with X-ray measurement from XMM Newton. We use the ratio of YSZ to YX as an observable, where YSZ and YX both are proxies of the thermal energy of the cluster ICM gas, but with different scaling with alpha. So to parameterize the temporal variation in alpha, we use the runaway dilaton model, and for special variation in alpha, we adopt a dipole parameterization similar to Gurley. And we use the same YSZ to YX ratio to constrain the deformed distant duality relation. For this purpose, we adopt 4 different parametric form of eta parameter. Also, in order to derive the luminosity distance, we use 3 independent techniques. First, using a redshift cut, and the second, non-parametric reconstruction from type 1 supernovae. And the third one is non-parametric reconstruction using cosmic chronometers. So in our conclusion, we found no significant temporal and spatial variation in alpha, and no violation in distant duality relation at 1 sigma significance. Thank you for having me.
Thank you, Kamal. Next talk is from Zhen Lin, if he's online. Or Sheng Lin, I'm not sure how to pronounce. Okay, I'm not sure he's online actually. I don't see him in the participant list. So I'm going to the next one. That's a pity. Enrique Cardoso.
Hello, my name is Henrique Lecieri, and I'm a master's student at the University of Londrina. Everybody's listening to me?
Yes, very well.
Okay. And in my work, I constructed a catalog of simulated cluster number counts using the cosmological library NumCosmo. And in each galaxy cluster in this catalog were assigned a real value for the mass and the redshift, and use these real values to create 2 proxies, one for the mass using a log normal distribution and one for the redshift using a Gaussian distribution. And with these 2 proxies, we calculated the observed variables for the mass and the redshift, which we use to perform a MCMC analysis together with a likelihood, which is the top one, to constrain the cosmological parameters and obtain very promising results. Every parameter agreed with the value given by the fiducial model used to construct the catalog, except for the little omega down here, but that was expected since the cluster number count data are not very sensitive to the equation of state of dark energy, which could have improved the result by adding new data, but that was not the focus of the work. And in the future, we will implement in NumCosmo a new likelihood, which will take into account the supersample covariance effect, and repeat this analysis to see the behavior of the estimators, and also perform a new Monte Carlo analysis to see if the likelihood will be biased or not. So thank you for everyone's attention.
Thank you, Enrique. Thank you very much. And then the last talk. The last talk is from Cameron Norton, if you're online.
Yeah, hi, my name is Cami. I'm a PhD student at New York University. In this research, we developed a new model for dark energy survey-like cluster analysis that is centered around the halo mass function. We write the HMF as a quadratic function with the halo mass function parameters, each quadratic in redshift. Then we add a single log normal mass observable relationship, giving us 12 parameters. We attempt to apply this to a DES Y1 data vector, which is composed of counts and log mean mass. And we find that the model is degenerate. The simple analytic form of the baseline model allows us to expose and understand these degeneracies. And in the end, to be able to invert the Fisher matrix and obtain constraints, we have to add a new piece of information, and we added the constraint on mass scatter. The image shows the parameter constraints we get. The best constraint parameter is the redshift derivative of the HMF amplitude, and the key degeneracies are shown on my poster. Thank you.
Thank you, Cameron. So I think this closes the poster session, the flash talk, except if Chen Lin is around, but I don't see him in the participant list. Too bad. So let's have a coffee break now. Lindsay, I'm not sure at what time we should resume because there is a hole in the program, I think. So should we resume at 18:55 or?
Yeah, 18:55.
Yeah, it's best. Okay. Yes, we have ample time. Yes.
18:55.
It's in 20 minutes.
So we have more time for yes.
17:55. Yeah.
Yeah, 17:55.
Yes. Yes. So
okay.
Oh yeah. Sorry. Yeah. Correct that right now.
Okay. See you.
See you.
And share. Stop sharing.
Hi, Bruno. Can you hear me? Hello, hello.
Hello.
Hello. Hi, Lindsay.
Hi.
Here's Mariana.
Hello. Nice to meet you virtually.
Nice to meet you.
Hello,
I would
Mariana.
like to. Hey. I would like to test, share my screen to check.
Yeah. Go for it.
Let me know if you can see my screen.
I can see it, but not on full screen. Also, your microphone went just a little bit quiet.
Okay. Let me.
Still a bit quiet, I'm afraid. Unless it's me.
Testing, testing.
That was much better. Yeah.
Okay, I was having some problems. My mic was varying its volume, but now I think it's okay. And I will put in full screen. Let me know if it works. Is it?
Yeah.
Does it work? It's okay.
Yeah.
And moving the slides, everything's fine.
Yeah, it looks good.
Okay. Well, thank you so much.
Very good.
Hello. Can I do a quick test?
Sure, go ahead.
Yeah.
Johan.
Okay, screen share. So what can you see exactly?
We saw it, but not in full mode.
Okay. Okay, no, can't do that.
Yes. True. Yes.
Is it okay?
That's okay. That's perfect.
Okay, excellent. So it's good. You can hear me as well. Good.
Yes, good sound.
Perfect. Thanks.
Okay, shall we start or wait a few minutes?
I think you could start.
Okay. Okay, so we're going to start the session which is dedicated to galaxy cluster detection and mass estimation in the context of upcoming surveys. So the first speaker will be Johan Comparat, and will talk to us about forward modeling for the structure in the X-ray by Eurosita. So Johan, would you like to share your screens? And yes, I will show this 3 minutes before the end of the talk.
Okay. The slides are just crashed, sorry.
No worries.
So we cannot see it's white.
Uh-huh.
It was working 5 minutes ago.
Yeah, the usual problems, I guess.
Demo effect.
Hopefully,
Yeah,
it's not what Erosita can see.
It's white noise.
Yeah.
Let's try again. Interesting. Okay.
Ah, okay.
Yes.
This one.
Perfect.
Okay, good. Yeah, sorry about the hiccup. So, hi everyone. Oh, right, now it's starting. Right. So I'm Johan Comparat. I'm a postdoc at Max Planck Institute for Extraterrestrial Physics in Garching near Munich. And in this talk, I'll discuss the forward model of the large-scale structure to be observed in the X-ray by Erosita. Right. So the motivation for the forward model is to go to better interpret the observations. And so on the left here, you see a field, a few square degree fields where you have events in black. And on this field are identified in red extended sources that are very likely clusters of galaxies, and as well as in blue point sources, likely AGN or stars. From this identification to work out cosmology, for example, we need to go back to a 3D distribution. So we need to infer the redshifts. So on the second panel here, you see the large-scale structure subtended by galaxies in gray, and then all these red dots where they go then in redshift, as well as the AGNs. Once we have this map and we understand completeness as function of redshift and possible systematics, and we measure the mass of each cluster, which is the topic here, we can compare the abundance of these clusters as a function of their mass with theoretical Hall mass function of dark matter halos, and put constraint in the plane of omega matter and sigma 8. And here represented, you see the latest XXL Paco 2016 contours, the latest Zubeldia CMB, so Planck contours, and the SPT from Bokeh contours, compared to the upcoming Erosita expected contours in 2023 in green, and in 2020, in orange, and then in green in 2025. So we're projecting that the uncertainties will diminish a lot, meaning systematic problems will kick in. And that's the reason why we put a lot of effort into forward modeling the measurement process so that we beat down all these possible systematic errors. Right, so here is how the motivation is, what I've just said: assess statistical and systematic uncertainties, understand selection function. That's key thing to understand. And also it's a neat tool for software validation, development, in particular source detection and extraction of source properties like the luminosity, the temperature, and so on. So here is the flow chart of pipeline. So we have models here, and I'll detail a bit more the models in this talk, and we have the observations here. And the models either feed in the pipelines we have for the observations, and then ultimately we have the selection function code and the scientific pipelines that can take either what the pipeline sped out from the observations or from the models from the simulations. So there are different components in the model. We have a light count, we have galaxy clusters, we have AGNs, stars, and we have a foreground or background diffuse emission. And quite a few references are starting to stack here. So numerical simulations, we need simulations to make the light count. So in this plane, you can see the result halo mass, 300 times the particle mass versus volume. The clusters of eROSITA, they're like above 10 to the 14 in halo mass, and they cover a large fraction of the sky that is not, obscured by the Milky Way. And so that's about this volume, a few times 10 to the 10 megaparsec cube. If we want to resolve the galaxies in the clusters, then we have to go a factor of 300 or 400 lower in stellar mass in halo mass, and we see here the galaxies in the cluster. So if we want one simulation to fit all of these tracers, we'd need a simulation with resolved halo mass of 10 to the 11, for instance, covering 10 to the 11 megaparsec cube. If we want to fit all the AGNs in there, we need to go further out in redshift, so the volume is bigger, and we'd need even larger simulations. So to get there, we'd need 40,000 cube simulations, which are now starting to be computable. But as of now, we're using 4,000 cube simulations, these multi-dark simulations. And in the near future, we'll use this 12,000 cube true simulation. Right, so here's how the cluster model goes. So the aim is to simulate the cluster both in the X-ray and in the optical. So to simulate the X-ray, we take clusters from XXL, XCOP, HighFlux, and XPT. We generate a covariance matrix between their mass, temperature, redshift, and emissivity profile. For all these clusters, we have these quantities. And so you see here where they are in the redshift mass plane. So they populate the massive, let's say, above 10 to the 14, we have a lot of tracers. Below 10 to the 14, it's a bit sparser, and we don't really have low redshift groups. So above 10 to the 14, we're sort of complete in terms of mapping this region. And in pink, you see what we project will be the eROSITA tracers. So on the right, you can see the covariance matrix between these quantities. You can see that the profiles are, the inner part of the profiles are covariant, as well as a little bit the outer parts of the profile are covariant. You see the scales of 0.1 to 0.3 or 0.5 are 500 here, don't have too much covariance, so this is good. You can see here you have mass and temperature. You can see some degree of covariance between mass and the outer part of the profile, so the overall, let's say, normalization, how bright it is, but there is no covariance with the inner part. So how it's cool in the inner part or not cool is not covariant with matrix, which is good. So with this covariance matrix, we can generate profiles, arbitrary number of profiles that will resemble the data set we've used to generate them, but it will be more smooth in sampling the probability space. So here you have an example sampling of emissivity profiles with cool core and non-cool core profiles. And you see here that the scatter is lower, and here it increases again. If we compare the scatter of this profile here shown here, intrusive scatter in blue, with Ghirardini 2019, we see there is a broad agreement between the red curve measured in a few XCOP clusters and the blue scatter we get. So it's an interesting proof to say, well, we get a reasonable scatter in these profiles. Then we look at the scaling relations to make sure we reproduce them properly. So here you have temperature, luminosity, scaling relation. All the points are from the data we've used to train the method, as well as other points like the Lovisari 2015, 20, and Bulbul 19, and Mons 16 that were not used in the sample. Only the Adami 18 is used. And you can see that the contour here is the projection, the prediction of the model, let's say. You can see that at low temperature or low luminosity, low mass, we tend to over predict luminosity. So this method works well above, let's say, 10 to the 14 in halo mass. So what we've done to generalize to groups is to use an empirical correction using the Anderson stellar mass to luminosity relation to correct at low mass let's say, the fact that the groups were too bright. And once the correction is applied, we can get a log n log s here in orange for above 10 to the 13, so even very small groups, that agrees with Spider, CDFS, Cosmos, and now the EFEDS LIU 2021 Eurozeta data. So this orange curve here shows that our number density of predicted cluster that will be predicted by the method is reasonable. So here is same thing, but the comparison of the luminosity function of EFEDS and the corrected method luminosity function, and you see the agreement is excellent. So that's for the clusters. Now, 2 slides on the AGNs. So for the AGNs, we take the same light cone with dark matter halos. We assign stellar masses according to the Beruzzi 2018 and 13 and 18 stellar mass to halo mass relation. And on top of that, we do halo abundance matching to give hard X-ray luminosity to each AGN, as well as a duty cycle. And it gives us, it reproduces by construction luminosity function because it's abundance matching. Right. Right, so what can still be changed here is the small scale clustering. We're studying right now what we could modify in terms of fraction of satellite, dependence on environment, and how it could affect detection probabilities. For instance, if you have more AGNs in dense environments, in like mergers, then this is now, we're investigating that. It's not clear yet how to constrain exactly these parameters. Right, the third component is the diffuse emission. So to have a realistic diffuse emission, we take the ERAS-1 data, we mask all the sources. So this is a map of the diffuse emission without any source, except for the really bright ones. And we resample from it to predict an observed flux at every pixel of the sky. So here it's the galactic plane, and there is a symmetry because Eurozeta D only has half the sky. And the good thing is, because we don't remove these really bright sources, it will be for sure excluded from areas we want to study. Right, so first application to Eurozeta EFEDS. So these first observations that were released in July. On the left here, you can see the EFEDS field and the exposure map. It's quite constant, about 1.2 kilosecond, 1.4 kilosecond. And you can see here the different spectra of these apertures here, from which we resample to simulate a background. So for EFEDS, we don't use the full sky background. Instead, we use a constant background over this 140 square degree area. And you can see here the real and the mock events as a function of energy. The curves are really close, meaning the methodology to populate the sky with synthetic photon seems realistic. And then here you can see the log n log s of the real point sources and the real extended sources in blue, and the mock ones. So it's also very close. It's hard to, let's say, quantitatively say it's different. Where it's a bit different is in the detection likelihood, and this is for the extended sources. The real extended sources, although they have the same log n log s, they are detected with slightly lower detection likelihoods, meaning that maybe our profile is a bit too peaked. So we might need to do some corrections here, that low mass profiles are probably too peaky, too cool. Right, so that's a great result. You can see in arXiv that the mocking method seems to be consistent with the observations. Then what we get out of that is we get a completeness and a spurious fraction. And here is for the point sources, you have these different curves that tell you you have for detection likelihood of 8, you're 70% complete and 1% spurious, and you can have these completeness maps. And the same goes for extended sources, for the clusters. And you can look, few papers coming up by Riccardo Seppi and Nicolas Claire, quantifying the same thing, the completeness fraction and the spurious fraction. So here I'm showing this green curve that's between 1500 and 3000 seconds. So typical ERAS 8 exposure with a detection likelihood of, so 40 counts, sorry. Then you can see that the average completeness is going to be about 80%, and the spurious fraction 1 or 2%. So it's saying this is going to be a good sample, a well-behaved sample for selection function. And here is the first attempt we've done to model the selection function with the color behind being the probability of detection and the red points, what we've detected in effects. So one other thing we need to constrain and is also the unresolved AGN population and its impact on AGN, on cluster scaling relation. So depending on the fraction of satellite in the AGN population, at high mass, we don't see a difference in the scaling relation, but at low mass, depending how far away we don't see the AGNs and they impact the luminosity of the clusters, at low mass 10 to the 13, 10 to the 13.5, we could have a small effect in the scaling relation, a small upshift. So luminosities are too high compared to what they should be due to AGN contamination. And on top of that, it increases the width here so that the standard deviation, the scatter in this relation, the, let's say, intrinsic scatter, has an additional component. So in red is the intrinsic scatter due to clusters only. And then in blue, and these three blue curves give different flavors of AGN model that say, well, you increase 2% or 4% or even maybe more than 10%, which, right. So we don't really know which curve to choose. It's likely more the cyan or the second blue. It's very unlikely to be this one. But we need more AGN studies to constrain these. Right, so not sure how long I have still. The summary is the following. So with Eurostar EFET's benchmark, we've validated our large-scale structural model of the X-ray, and they are now accurate. So you can find the description in Comparat 2019 and 2020. The detection function is optimized for point sources and extended sources. So for EFET, we've done 20 rounds of simulations before we got to what I showed you now. So we expect that for ERAS, the all-sky survey, we'll also get there with hopefully a lot of simulations. And the cluster selection function is being quantified right now by Seppi and Clerc. The prediction of the scatter term in the cluster scaling relation, depending on AGN, is still to be entirely determined. And right, so that's for the results we have now. The next task are the validation of the luminosity and the temperature and redshift measurement for the clusters on a very large area, and investigation of systematics due to observational patterns, so the attitude, the foregrounds, the NH maps, as well as the EBV and the depth maps in the optical data we use to infer redshift. And the final task, and hopefully we will complete that in 1.5 years from now, is the inference of cosmological parameters with the ERAS-1 map.
Okay,
yeah.
Thank you very much, Johan. So time is over. There is time for one question. So I see, well, two. David Turner.
Hi. Thanks for the talk, Johan. It was nice to be able to hear about this again when I could actually pay attention. But basically, I was wondering, I'm assuming some sort of PSF characterization goes into your simulated observations, etc. But basically, I was wondering whether, because it's such a new instrument, relatively speaking, has the PSF been properly quantified yet? Like Reed et al. For X-Men did it in 2 dimensions, a very comprehensive study. And if so, because I know the E-Rosita PSF is relatively large in terms of the spreading effect, do you expect it to have much of an effect on your completeness or purity measurements or predictions from your simulations?
Yes, so the simulations are photon simulations. So we simulate the full instrument and
of course,
hopefully all possible details of the instrument. So the simulator is called 60. It's developed at Bamberg. It's a publication by Thomas Dowser in 2019. It's an extremely detailed description of the instrument. There are some differences between telescope modules in the true telescope that are not yet implemented in the simulator. So the simulations are a bit optimistic in that regard, that 2 telescopes, right, because you have on-chip filters on all telescopes except for 2. And so these are not completely simulated yet, and it leads to some, say, light leaks that have an impact. But so far, these are handled by the software, meaning after data reduction, we see small differences, but they're not like drastic.
Yeah.
So yeah.
Thank you very much.
Okay, so one last question by Bruno.
Well, it's a related question, actually. Just so you mentioned that the selection is optimized for detection of extended sources, but in your selection function, it only was a function of flux. So how do you, because a lot of care was put for the XXL, you know, to take the extension, but did you do that also for?
Oh, yes, so it's I showed one figure to, it's illustrative, but the selection function is multivariate. It's in many dimensions.
Okay.
It's not, so we have, let's say, forward model selection functions that take halo mass, redshift, temperature, and so on, theoretical quantities. But we also have selection functions that take in observed quantities. So detection likelihood, extent likelihood, number of photons. And so, right, so these are, let's say, complementary, and this is just a projection in one dimension of the multivariate.
Okay, I missed that, sorry. Great.
Okay, so thank you very much. So we are going to move on to the next speaker, who is Mariana Penna-Lima, who will talk about cluster cosmology and self-calibration in the LSST era. So Mariana, would you like to share your screen?
Yeah, can you hear me?
Yeah, yeah.
Can you see my screen?
Yes.
And full, let me check full screen now. It's okay?
It's
okay. Good. So good afternoon, everyone. Thanks to organizing for the opportunity. I am a professor at the University of Brasilia, and my name is Mariana Penna-Lima. So during this week, we have been learning about different methodologies that we apply for cluster cosmology, mass calibration, or the study about the astrophysics of clusters. And these methodologies include binary and unbinary likelihoods for cluster counts, clustering, mass calibration. We have also the pseudo-cluster counts, which is an unbinary approach when we don't know the selection function. And we have also a likelihood-free methodology, which is approximate Bayesian computation. And today we had lots of great talks about machine learning and its application on cluster studies. This plot here, I show the constraints on mass and concentration parameter obtained from two different likelihoods. The purple one is from an binary likelihood from reduced shear signal, and the blue one, the blue contours, we obtained from a binary likelihood, and this result is obtained in the CLMM work. Many of us here are present in the conference, and you can also see Alex poster for more details. About the pseudo-counts likelihood approach, for example, we have applied this methodology using 21 clusters from Planck and Clash clusters, and we fit, as I mentioned, this approach is useful when you don't know the selection function for your catalog, and this methodology is also nice because you can put all information about the mass observable relations, if you want cosmology, the selection function, and fit all together. So here is our result, here, Clash, and you can see that we obtained larger error bars than other studies, which show the sample size, but also because my volume is too high or too low? Low?
High.
Let me check here. Is it better? I hope it stays. It's okay.
The sound disappeared.
Okay, but you can hear me now? Can you hear me?
Yes.
Okay, so
There is a little background, but okay, go on.
let me check.
Before. Something must have changed.
Okay, let me check. It's okay? Is it okay?
Yes, yes, yes.
Okay, okay. Sorry about that. So here our error bar.
No, we cannot hear you. Can you speak again?
Yep. Let me check. I think it's the contact here. Can you hear me like this?
Yeah, yes, but
Okay. Oh. Oh, thank you. I changed the phone. I hope it works.
Yes, it works now.
Okay, sorry about that.
Not worry.
So here I would like to emphasize that we are fitting lots of parameters, 11 parameters, and some of the other studies fix, for example, the lensing information, the slope and bias of the lensing mass relation. So moving on. What I want to emphasize here is that we have a lot of uncertainty sources to perform the studies with cluster, and we know and we deal with them. We have the photometric redshift error, the cluster mass when we do cluster cosmology, the multiplicity function error. We get the antibody simulations results. So we, for example, Tinker provides a 5% precision at a redshift 0. The SPALI has shown that we get a universal multiplicity function if we define mass in terms of virial radius. Sebastian performed some studies including baryon effects and also provided the multiplicity function for different mass definitions, and considering critical mean density. And McClintock has provided 1% precision at redshift 0, and this for current analysis, this is not so important. So, but for example, for the next generation surveys like LSST, Euclid, we have to get a better precision even at this point to carry out the analysis. Other uncertainty sources, we have the bias on the parameter estimators. This is not usually checked in many studies, but I have carried out an analysis using cluster counts likelihood, and we show that some parameter estimators have bias, and they can be really relevant depending on the maximum redshift, survey area, photometrical spectroscopic redshifts, the mass uncertainty. So this is something that we have to pay attention. And independently of the approach we use, we have to take care also if the cosmological parameters are biased or not in our analysis. Other sources of uncertainty comes from the halo profiles. We have to define inner and outer profiles. We have different parameters and concentration relations, splashback and truncation radius. And all of these questions we can study along with cosmology and mass calibration, but it can also, if we make some assumption, we have to take it into account in our analysis. And what I want to focus here is the numerical precision, because LSST and Euclid will bring lots of an amount of data that is completely different from the current the surveys that we have. So we have to take care about it. So here I want to discuss that we have the pipeline we have to perform this analysis. We come from theory, and here I mentioned some public codes such as Numerical Cosmology Library, the Core Cosmology Library, Colossus, and Cluster Toolkit, for example. There are others. And along with the theoretical computation, we have the external data from cluster. We have lensing, richness, SC, X-ray. And given these two bases, we will perform a statistical analysis to obtain the constraints on cosmological or mass parameters. So what is important, we have, I want to highlight here that it's really useful for our community to have public codes that can be extensively used and tested. And this is one of the main goals here. So, for example, I show here the comparison between the mass function that we compute from non-Cosmo and CCL. You can also see Cynthia Nunes post. And here we have on the right panel, we have Pratchester, Schacht-Dorman, Jenkins, Tinker 2008, and Tinker 2010 mass functions. And here in the bottom, we show the relative error between the two computations. And on the right panel, we have the results for bokeh multiplicity function, given the different hydro simulations or dark matter only simulations and the different mass definitions that they provide. So here you can see that we have an agreement between both libraries about 10 to minus 5, and this increased for large masses. And you can think, okay, but these are the multiplicity function, fitting functions. We would expect better agreement between them. So this relative error between the two libraries come from mainly the computation of the variance of the meta density contrast. So I'm going to discuss this a little bit. We are trying to compare all functionalities of both libraries. So to assure that all computations, even from Hubble function, cosmological distance, everything works properly and provide the good results, numerical results. And another thing that we care here is the computation time, because the data vector here is going to be huge for Euclid, LSST. So some analysis that we are carrying out today will not be feasible in the next service, even because we need more precision level on the numerical computations. Another example is about the halo profile. Here we show the sigma and also the excess sigma from CCL, non-Cosmo, and Cluster Toolkit libraries. Here we show the results for NFW, both analytical and numerical computation. We use as a base here the analytical NFW and compare with the numerical computations using NFW profile. And on the right panel, we have Inasto and Henrique's profiles. So we show here that non-Cosmo provides a good result, better than 10 to minus 8. And for the other libraries, such as Cluster Toolkit and CCL, the precision level is much smaller than 10 to minus 3, and this could be a problem for LSST, for example. So we have to compare and see what are the assumptions. For example, CCL, we use FFT log, fast Fourier transform technique, and we are verifying that if we increase if we adjust the parameters to obtain a better precision level, we have the code becomes too slow. So we also don't want it. So we have to have this compromise to compare execution time and precision level and deal with it. And the same we have here for the other halo profiles. Okay, and for example, between Colossus and Cosmo, we have a precision to 10 to minus 6 or better. And another example, the execution time to compute delta sigma using cluster toolkit is 2.5 times slower than Cosmo. So this is the kind of analysis we are performing, comparing these public libraries to identify where we can do better and determine the precision level of each computation of the cosmological or cluster quantities. So to conclude, here we, as I mentioned, we are comparing at least 2 independent codes, Cosmo and CCL, and in DESC, our SST, we intend to carry out all analysis using both codes independently, and we are validating all functionalities of both libraries using another libraries that are available. All these cross-checks we are writing in Jupyter Notebooks format, so they are available for the community. And I encourage you to use these public codes and contribute if you want. You can ask us how to use, how you can join your codes with non-Cosmo or CCL, or even to become a developer in both libraries. Okay, we want here to increase the numerical precision of our computations and also having a good execution time to perform the analysis we are going to do in this service. And we also implementing optimization techniques. So for example, another thing comparing CCL and Cosmo, we have in Cosmo the determination of the knots to perform spline interpolation. We compute it automatically given a required precision level. So this is something that we noticed that it's really efficient. So we are now want to implement it also on CCL, for example. And as we are, I did not mention here, but NumCosmo also provides the statistical analysis tools. So it's in preparation. It's a work in progress by Vicente and Eduardo Barroso, simpler that it's showing that it's really efficient in comparison to other codes that are highly used in the literature. So that is it. Thank you for your attention. And sorry about the microphone problem.
Thank you very much, Mariana. This is for your very interesting talk, and I think this is really very useful to have all this comparison.
Thank you.
I am looking for some questions.
There's a question from Gary.
From Gary. Okay, Gary, please.
Hi, Mariana. That was very nice.
Hi, Gary. Thank you.
So I was intrigued by the one slide you showed where you showed the concentration mass relation calculated using binned or unbinned likelihoods, and the difference was huge. And I think we discussed this at one point in the Euclid cluster cosmology pipeline. We've been having a debate on whether we should use binned or unbinned likelihoods. And I've been favoring unbinned likelihoods just because the number of clusters at very high mass drops fast, and the number of clusters at high redshift drops fast. And so the way we bin the redshifts and the way we bin the masses will change our results. But the people who favor binning, they say if we want to do Fisher matrices to combine this information with other cosmological estimators like cosmic shear and clustering, we will need to use binned likelihoods, which is something I don't really understand. So what is your feeling about that?
Yeah, my opinion is that if it's possible to broke your analysis, you do unbinned, you perform an unbinned analysis. If you have enough information, you should use it. And for example, if you have a cluster catalog from mass from 10 to 13 and to 10 to 15, let's say, you should broke it. And for smaller clusters, you perform a binned analysis and join it with an unbinned likelihood. But at first, I think you should do an unbinned likelihood to use all information from your data.
And for the Fisher matrix, they can use the observed Fisher matrix.
Oh, yes. Sandro is mentioned here that for Fisher matrix, you can use the observed Fisher matrix. So in this case, the data you will enter in the analysis.
But is that doable for 100,000 clusters and cosmic shear on a billion galaxies and clustering on a billion galaxies? I don't know.
How many clusters? Sorry.
100,000.
100,000. Yeah, it's huge. So this is what we are discussing and trying to make it feasible to use a big sample and be able to perform an unbinned likelihood.
1 second for 10,000 clusters.
1 second for each step.
Yeah.
So each step of the parameter space, for example, we
integrate over 10,000
clusters over 1 second using weak length information for mass estimation. Yeah. So I think it's feasible.
Depends on how many integrals you have in your likelihood. Yeah.
Yeah.
You know, we've been talking about anywhere from 1 to 6 so far, right? So
yeah.
Okay, so I saw Johan's hand up, but I don't know if you still want to ask a question or if it was not anymore.
Yes, I was wondering if you had comparisons with the dark quest emulator from Nishimichi et al.
Not yet. And please, if you could send the reference, please, it would be great. Because as many codes we know and we can cross-check and validate everything, it would be great. And please, if you are interested, join into the pod.
Sounds good.
Okay, so thanks, Mariana. So
thank
time
you.
is flying. So we are going to hear Matteo Maturi, who is going to tell us about Amico, Cluster Finder, and the perspective on surveys. Okay, so Matteo, I saw your presentation. I cannot see it anymore.
Yes, I lost it a second. Sorry. Okay, I'm back. Okay, hello everybody. Thank you very much for the invitation. It's a pleasure to speak here. It's a nice audience. So I hope to have some nice feedback and discussion with you. So please, Sophie, call me when I'm 3 minutes. When 3 minutes are left, I don't want to cut the discussion after. So please really call my attention if I'm running long. Okay, so I'm going to discuss about Amico and what we are doing with this algorithm with various surveys. And I mean, you know that what we need to do is to understand astrophysics, to do cosmology, and we also as well need cosmology to do astrophysics. And to do that properly, we need a selection function, which is which must be a solid estimation for the selection function. So to do all of this, we start with the detection of clusters with Amico. That's a detection algorithm. And the selection function is based on Sinfonia. So I will mostly speak about the methods that we developed and that we are using, and then I will show few applications to KIDS, JPass, and Euclid. I will skip DES and LSST for now. Okay, so that's about cluster detection and object detection. You use your telescope, you point it at the sky, you get your nice pictures, and then you forget about them, because what you actually use are not the nice pictures. So it's not some machine learning that's starting from the images as we have seen in previous lecture, in previous talks, but we are processing a catalog of galaxies. Therefore, there is a pre-processing in which all galaxies, stars are identified, the two classes are separated, and then we just work with the galaxy, the catalog of galaxies. We are now with a galaxy, we have to think about it in terms of a vector. So one galaxy is a vector. Each property of the galaxies is one of the entries in the vector, okay? So we need to turn the galaxy into a mathematical element such that we can apply Amico, which is based on a matched optimal filter, in which, as I said, galaxies are meant to be, one galaxy is at one point in an n-dimensional space, where the number of dimensions is arbitrary and can be as abstract as you want. Could be as well derived properties such as stellar masses, magnitudes, colors, or whatever, okay? So how does it work? We first model the data as it's written up here. So we have the signal, which is basically the contribution given by the galaxies belonging to clusters, plus the noise, which are the galaxies belonging to the field, basically. The model of the cluster, the signal, is basically composed by two main components. One is this A factor that scales the amplitude of the cluster. So larger is the A, larger is the number of galaxies belonging to a cluster. And then this tau factor, which is this tau function, which incorporates the behaviors of the properties, better to say, of the galaxies within galaxy clusters, okay? So as I said, tau is not a position, it's a completely abstract value. And at the moment, for the applications that I'm going to show you, even despite Amico could work in an n-dimensional space, we restricted our application to a radial density, radial distribution. So with where the model of the cluster is given by an NFW profile. And then we're not using colors, but we are just using one magnitude. Okay, we could use n magnitudes. In this case, we're only using one magnitude. And the information that is incorporated in the model is the luminosity function of clusters. Okay, then the properties of the noise are extracted from the data themselves, and they must mostly capture the same properties in terms of luminosity function and density of the field galaxy. So it's basically a power spectrum. Okay. Then once we have our model of the data, we define our estimator, which is just a simple linear estimator in which we have a kernel function that is unknown, is arbitrary. This could be a step function or whatever. What we're using is a minimization constraint approach that maximizes the signal to noise ratio, retrieving at the same time an unbiased estimate for the number of galaxies belonging to clusters, so this factor A. Once we apply this mathematical approach, there is an answer that is going to tell us the best filter to achieve minimum variance and being unbiased estimate is this filter. Okay, so it's a solid and clean mathematical structure that is basically as a background for Amico. So this is how the filter look like. So you see there is the constant, a normalization constant we don't care about. Then there are basically an F function that captures all the properties of clusters in terms of luminosity function, radial distribution, and so on. And then a covariance matrix that captures the behavior of the noise. As you see, there is an inverse, so you can think kind of a ratio of your signal with respect to the noise. And you understand that where the properties of the galaxies are dominant, belonging to the clusters are dominant with respect to those of the field, the values of the filter is larger with respect to the case in which the dominant, the noise is dominating over the noise. Then those sort of galaxies are suppressed by the filter in an automatic way, if you wish, in an optimal sense. So this is, as I said, is an n-dimensional space, two-dimensional in this case. If we slice into the magnitude space, you can see basically the luminosity function of clusters in red, the one obtained from the data for the field galaxies in blue, and the filter one is basically the input that the information that Amico uses to create the optimal weighting for the galaxies in terms of magnitude only, in this case. And you see that it's basically giving privilege to bright galaxies, but it's not trashing the fainter galaxies. So it's using all information you have in an optimal way in this sense. Okay. Then what we do after we swallow our catalog of galaxies, we filter it through the filter. We get this three-dimensional map where we have Ra, Dec, and then redshift. So it's a three-dimensional map of a representation of our universe. We identify the blobs with the largest signal-to-noise ratio. And then Amico is also providing the probabilities for the galaxies to belong to each detection. And then using this information, we can remove the detection. Then what we do, we go for the second most likely clusters, we find it, and so on and so forth, until we arrive at the end of the process where we find all the clusters that are present or visible, better to say, in the data. These are a few examples from data release 4 in kids. In which I can show you can see the kids images on the top, the filter response given here by the ISO contours, and on the right hand side you can see the galaxies that have been identified by Amico as belonging to the clusters, with where the color is proportional to the probabilistic association of the galaxies to the cluster. So the yellow ones are more likely to belong to the cluster than the other ones. Okay. Here, just to show you a comparison, that's the same cluster, but in a Subaru image. Okay, so this detection of a cluster at redshift 0.91, we did it with kids. Here you can see what you could do with the HSC. So we are going to run Amico also on HSC, and I'm looking just at the difference between the images. You understand that we are going to find very likely many clusters at higher redshifts. Of course, the probability association we tested against spectroscopy. So you can see the probability given by Amico and the one given by spectroscopy, and it's very well in line with the expectation with spectroscopy. So it's quite a solid estimate. Moving forward, this is detecting galaxy clusters. Then we need to establish the selection function if we want, for example, get cosmological constraints through number counts. So this is the actual numbers of clusters. This is the number of clusters that we detect, that are basically the real number of clusters that we have, swallowed, convolved by the selection function that we need to estimate to have a full access of the data and cosmological constraints. So the way we do it, the philosophy that we embedded in our pipeline is a data-driven approach that is implemented in Sinfonia, that stands for Selection Function Extractor. Basically, the idea is to start from the data sets, use a probabilistic association of galaxies to clusters. In this case, we are using Amico, but any kind of probabilistic association can be used. The algorithm split the sample into samples, one in the two field galaxies, where all galaxies is extracted randomly, weighted according to their probability to belong to the field. And this creates a universe in which there are no clusters, based according to this probabilistic association. On the other side, we collect into bins of clusters of redshift, richness and redshift, of all the galaxies that have a probability larger than 0 to belong to clusters. And then we perform a similar random extraction to generate clusters out of it. Okay. Once we have that, we can basically create a universe in which we know where the clusters are, or everything based on the data only. This is an example of representation of these mocks, where on the right hand side, where all the masks, absorption features, and that you have in the data and so on are reproduced because they are coming from the data, as well as the photosys that are very difficult to model. They are real photosys, and therefore they are accurate with respect to that. Once you have your mocks, you can run Amico, your detection algorithm, then, and estimate the selection function, uncertainties in redshift, in lambda, in the richness, and so on and so forth. So for testing and assess the accuracy of your measurements. This is to show you the effect of the selection function. So yellow lines will be when you do not apply the selection function on your number counts. And then you see the black points once you apply the selection function. So you see that the impact is only relevant for low lambda clusters, so small clusters. So the others, of course, you have you find all of them, and therefore the selection function is not playing any role there. Few application. So that's JPAS. That's a survey. The telescope is sitting in Spain. It's a 2.5 meter telescope. And the peculiarity of this survey is a very good thing of this site that's sitting in Spain, but the site is extremely good. Look at the PSF that is in median 0.71. And the peculiarity is the fact of that at the camera, there are 56, in front of the camera, there are 56 narrowband filters. So it's, you can say that it's a photometric survey, but it's almost a spectrographer. Okay, you can also imagine it, you can think in terms of a low resolution spectrographic instrument that provides extremely good photometric redshifts. There are few, the camera is just in place. They are starting to take data right now, but we already have 1 square degrees with a Pathfinder camera with all the filters. So we had the possibility to test our algorithms, among which Amico. So you can see here the distribution of cluster that we detect. Look at the accuracy in the photosys, that's 0.004. So that's 10 times better than what we did with kids, for instance. So it's extremely, it's amazing what it can do in terms with redshift and in terms of sensitivity with respect to mass. Here we basically matched our detections with X-rays estimates. So because on these fields there are Chandra and XMM data that we use to produce mass estimates, and look at the mass that we can detect. So you can basically, with this machine, you can have a good scaling relation for individual clusters for masses that are on the order of 10 to the 13 solar masses. So that's quite relevant. Thank you.
2 minutes.
Thank you. Then moving on, another example is KITS, that's the kilodegree surveys. So far, we fully processed the data release 3. That's roughly 400 square degrees, where we have 8,000 clusters. So if you wanted, the data, the catalog is available on request. So just not to have superposition with ongoing projects. So if you want, just ask us and we can agree for sharing the catalogs. It's 80% complete and 95% purity. So it's a pretty good catalog, I have to say. And ongoing, there is the analysis of the data release 4 of KITS. That's a much larger area, so at 800 square degrees, more than double. And with much better photosys, because in this case, we have also Viking that provides infrared data with much better photosys that give not only better location in terms of redshift, but also in terms of depth, because kind of clusters along redshift are more compact in the parameter space, and therefore they can be better identified, and therefore give us the possibility to go lower in terms of mass. But this is an ongoing effort. So Giorgio already showed you the results with respect to cosmology that we obtain with data release 3. What I would like to stress of this analysis is the fact that we could get the scaling relations, not only from weak lensing analysis, so just by direct mass estimates of the clusters, but from the clustering analysis. So we looked at the clustering of galaxy clusters and we let free the parameters constraining the scaling relation, and we got scaling relations that are very well compatible with what we got with gravitational lensing. So this makes us believe that the sample is a solid one, and it also showed that how it's also possible to get reliable measurements for the scaling relations without gravitational lensing, or if you wish, in addition to gravitational lensing. And we did astrophysics. I don't want to speak about it. Here is just to show you the much better quality of the data release 4 in terms of depth and area. That's also what Giorgio showed you. You can see that the peak shift to lower lambda star, meaning smaller clusters. So we can see smaller clusters. The accuracy of the photosys is improved by a lot, and you can clearly see it here by comparing the two redshift distribution of the detections in data release 4 and data release 3, where this hole disappeared, and this is given just by a feature of that is typical for the transition of the 4000 break between the G and R band that create confusion in photosys. We don't have that in DR4 thanks to the infrared data. So the quality is going to be much improved in this new release that is upcoming. And in this case, we are going to have 20,000 clusters with synchronous ratio larger than 3.5 in this redshift range. Not only these clusters, we pushed our search to even higher redshift, up to redshift 1, and where we are actually finding real clusters is not dominated by noise. This is an example of a cluster at redshift 0.91. and the probabilistic association of amico. And this is another detection that we found. It looks like a real cluster, but it's not in the ACT sample. So ACT is overlapping our survey. We are also finding clusters that ACT didn't find. And here you can see basically the fraction of clusters that we find at ACT. So 90% of them, more than 80, between basically 90% of them up to redshift 0.8. And then there is a drop in sensitivity, but also this is also given by the fact that, for example, here you see that we have a completeness of 50%. That's because there are two clusters there of ACT. So one we find it, the other one we don't. Okay, so that's pretty solid also at a higher redshift.
Matteo,
Last one, Euclid.
Go quickly to the conclusions.
Yeah, I conclude here. Euclid, this is just you know, it's an upcoming survey where we basically Amico won an internal challenge and is now one of the two detection algorithms implemented in Euclid. You can see here its performance with respect to, well, let's just look at this plot of, between purities and completeness. You can see it's more pure, so it stays above, and it's more complete, stays more on the right-hand side with respect to the other algorithms that run in the computation. So it's a pretty solid algorithm. Currently, we are basically in the phase of implementing the algorithms, both Symfony and Amico, into the pipeline. And we are going to run the full pipeline on HSC to make a full test of our pipeline. Here I leave you to my conclusion. So again, if you want to have the catalog for data release 3, just get in touch with me. And yeah, and I show you Symfony and our applications to the 3 services that I'm depicted here. Thank you.
Thank you very much, Matteo, for your talk. And I'm looking forward to see the results of Amico and Euclid. Are there any questions in the audience? Johan?
Hello. Yes, I would have 2 questions about the resimulation using data. So I understand you shift real clusters somewhere else in the data. So I believe this would then have the effect of isolating the clusters from the large-scale structure. Is that an issue then when computing statistics? Do they look better or worse?
No, so what we basically do, we fully reproduce the statistics of the data one-to-one by construction because both the realization of the clusters and of the field galaxies go through the same probability. And the sum of the probabilities of galaxies belonging to one or the other is 1. So on average, we fully reproduce the statistics of the clusters. So what we do is after we split so basically there are 2 runs. So in one, we basically remove statistically the clusters and we create just the field galaxies. Then we can shift a little bit the galaxies and we can play a little bit with them as we want. But on a scale such that we do not erase the large scale structures, but we want it at the scale of this reshuffling large enough such that if there are clusters left in our sample, we remove them so that we have a clean field galaxies. On the other hand, for the clusters, what we do is to generate clusters by, again, similarly randomly picking galaxies from bins of redshift and richness for the cluster that we want to generate. And then we locate them. What we did was to locate them near to the original position of the clusters that we detected. Okay? So in this way, we keep the correlation between the large scale structures. Again, we shift them a little bit because we want to improve the randomization of our mocks, but we want to keep all the correlations that are in the data as they are.
Okay, thanks.
Okay, so thank you to everybody for participating to this session. So now I believe we are going to pass at the discussion.
Yes. So we had a pretty intense day, but let's try to entertain ourselves for half an hour or so. So I and Sophie we are going to moderate the discussion. So we decided to split into 2 blocks. One covering the first topic, which is machine learning applications, and the second, next generation surveys. so let me start, the first theme. So I'm going to share my